In the collective imagination of humanity, Pluto holds a place unlike any other world in our solar system. For 76 years, it reigned as our ninth planet, the distant guardian at the edge of known space. Generations of children memorized its name, drew its orbit in school projects, and dreamed of what mysteries might hide on that frozen, faraway sphere. When astronomers reclassified Pluto in 2006, the public outcry revealed something profound about our emotional connection to this tiny world. Section 1. The Cultural Legacy of Pluto. There is something deeply personal about Pluto that transcends its physical characteristics. Perhaps it is the story of the underdog, the smallest planet that always seemed to be trying its hardest to belong among the giants. Perhaps it is the romance of distance, the knowledge that sunlight takes over 5 hours to reach its icy surface, making it a world perpetually bathed in twilight. Or perhaps it is simply that Pluto was discovered within living memory, making it feel somehow more human, more accessible than worlds known since antiquity. The attachment people feel toward Pluto became abundantly clear in August of 2006, when the International Astronomical Union voted to reclassify Pluto as a dwarf planet. The reaction was immediate and emotional. Protests erupted, not from scientists alone, but from ordinary people who felt that something precious had been taken from them. State legislatures passed resolutions declaring that Pluto would always be a planet within their borders. Bumper stickers appeared on cars across America, proclaiming loyalty to the demoted world. The intensity of feeling surprised even astronomers, who had approached the reclassification as a matter of scientific precision rather than cultural significance. This emotional response reveals something important about how we relate to the cosmos. The planets are not merely objects of scientific study. They are characters in the story we tell ourselves about our place in the universe. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune have been known for centuries or millennia. Their names drawn from ancient mythology, their movements tracked by countless generations of sky watchers. But Pluto was different. Pluto was ours. It was discovered by an American, named by a British schoolgirl, and embraced by a world hungry for new frontiers in the aftermath of the First World War. The story of Pluto is also a story about the evolution of scientific understanding. When Clyde Tombaugh first spotted that tiny point of light moving against the background stars in February of 1930, astronomers believed they had found a world perhaps as large as Earth. Over the following decades, as telescopes improved and observations accumulated, Pluto seemed to shrink. First it was smaller than Earth, then smaller than Mars, then smaller than our own moon. By the time the New Horizons spacecraft arrived in 2015, we knew Pluto to be a world just 2,377 kilometers in diameter, smaller than the distance from New York to Los Angeles. Yet this diminishment in size was accompanied by an expansion in wonder. The Pluto revealed by New Horizons was not the dead cratered ball that many expected. Instead, it was a world of stunning complexity, with towering mountains of water ice, vast glaciers of frozen nitrogen, a hazy blue atmosphere, and a heart-shaped feature that captured the imagination of millions. The spacecraft's images showed a world that was geologically active, constantly renewing itself through processes that scientists are still working to understand. The cultural significance of Pluto extends into music, literature, and art. Composers have written symphonies inspired by its distant solitude. Authors have set science fiction novels on its frozen plains. Artists have imagined what it might be like to stand on its surface and gaze back at a sun reduced to merely the brightest star in a dark sky. Pluto has become a symbol of the unknown, the unreachable, the mysterious edges of our solar neighbourhood. In classrooms around the world, the debate over Pluto's planetary status has become a teaching moment about the nature of science itself. Students learn that scientific classifications are not handed down from on high but are human constructions, subject to revision as our understanding grows. They learn that reasonable people can disagree about how to categorize the natural world, and that such disagreements are not failures of science, but evidence of its vitality. Pluto, in its ambiguity, teaches us that the universe does not always fit neatly into the boxes we create for it. The journey to understand Pluto has spanned nearly a century, from Percival Lowell's mathematical predictions in the early 1900s to the New Horizons flyby in 2015 and beyond. It is a story of patience and perseverance, of technological innovation and human curiosity. It is a story that begins with a wealthy astronomer's obsession and culminates with a spacecraft travelling faster than any bullet, carrying the ashes of the man who first glimpsed this distant world. As we prepare to explore the complete story of Pluto, from its predicted existence to its discovery, from decades of mystery to its stunning unveiling, we embark on a journey that is both scientific and deeply human. This is not merely the tale of a celestial body, but the chronicle of our species' endless desire to know what lies beyond the horizon, beyond the visible, beyond the easily understood. Pluto, in all its frozen glory, represents the frontier spirit that has driven exploration since the first humans looked up at the night sky and wondered. So settle in, allow your breathing to slow, and let the story of Pluto carry you gently through the history of one of humanity's greatest astronomical adventures. From the observatories of Arizona to the frozen plains of the Kuiper Belt, from the hopes of early 20th century astronomers to the triumph of 21st century space exploration, this is the entire story of the world that captured our hearts and refused to let go. Section 2, The Hunt for Planet X, Percival Lowell's Dream. The story of Pluto's discovery begins not with Pluto itself, but with a mystery, an unexplained wobble in the orbit of Uranus that had puzzled astronomers for decades. To understand how Pluto came to be found, we must first travel back to the 19th century, to a time when the solar system seemed to be revealing its secrets one by one, rewarding patient observers with new worlds hidden in the darkness. Uranus, the seventh planet from the Sun, was itself a relatively recent discovery when astronomers began noticing something strange about its motion. William Herschel had found Uranus in 1781, the first planet discovered with a telescope rather than known since antiquity. As astronomers tracked its orbit over the following decades, they noticed that Uranus was not quite where their calculations predicted it should be. Sometimes it moved slightly ahead of schedule, sometimes slightly behind. These discrepancies were small but persistent, suggesting that some unseen influence was tugging at the distant world. The solution to this puzzle came in 1846, when mathematicians John Couch Adams in England and Urbain Le Verrier in France independently calculated where an unknown planet must be located to produce the observed perturbations in Uranus's orbit. When astronomers pointed their telescopes at the predicted location, they found Neptune, a triumph of mathematical astronomy that seemed to confirm that the solar system operated like clockwork, its secrets yielding to careful calculation. But the discovery of Neptune did not entirely solve the mystery. Even accounting for Neptune's gravitational influence, small discrepancies remained in the orbit of Uranus. Some astronomers believed these residual perturbations indicated the presence of yet another planet, even more distant than Neptune, lurking in the outer darkness of the solar system. This hypothetical world came to be known as Planet X, and its pursuit would consume the final years of one of America's most colourful astronomers. Percival Lowell was born in 1855 into one of Boston's wealthiest and most distinguished families. His brother Abbot Lawrence Lowell would become president of Harvard University, and his sister, Amy Lowell, would win the Pulitzer Prize for poetry. Percival himself seemed destined for a life of comfortable privilege, but he was possessed by an insatiable curiosity about the cosmos that would lead him far from the drawing rooms of Boston society. After graduating from Harvard with distinction in mathematics, Lowell spent years travelling in the Far East, writing books about Japanese and Korean culture that were widely read and admired. But in his late 30s, his attention turned decisively toward astronomy, specifically toward the planet Mars and the controversial question of whether it harboured intelligent life. In 1894, Lowell established an observatory in Flagstaff, Arizona, choosing the location for its clear, steady air and dark skies. The Lowell Observatory was built primarily to study Mars, and Lowell spent years mapping what he believed were canals on the Martian surface, evidence of an ancient civilization struggling to survive on a dying world. His theories about Martian canals were controversial, even in his own time, and have since been thoroughly disproven, but they captured the public imagination and helped inspire generations of science fiction. As the years passed and the canal controversy consumed much of his energy, Lowell became increasingly interested in the outer solar system. The residual perturbations in Uranus's orbit nagged at him, suggesting that the solar system might contain worlds yet undiscovered. Beginning around 1905, Lowell began a systematic search for Planet X using mathematical calculations to predict where such a world might be found. Lowell's calculations were based on the assumption that the perturbations in Uranus's orbit were caused by a massive planet beyond Neptune. He estimated that Planet X would be about 7 times the mass of Earth and would orbit the Sun at an average distance of about 43 astronomical units, where 1 astronomical unit is the distance from Earth to the Sun. Armed with these predictions, Lowell initiated a photographic search of the sky, hoping to catch the slow motion of the distant planet against the background stars. The search for Planet X was painstaking work. Astronomers would photograph the same region of sky on different nights, then carefully compare the photographs, looking for any point of light that had moved. In an era before computers, this comparison was done by eye, using a device called a blink comparator that rapidly alternated between 2 photographs, causing any moving object to appear to jump back and forth. Lowell pursued this search with characteristic intensity, but Planet X eluded him. Year after year, the photographs accumulated, but no new planets emerged from the data. The work was tedious and often frustrating, requiring endless patience and meticulous attention to detail. Lowell drove himself relentlessly, convinced that discovery was just around the corner. The strain of the search, combined with his other astronomical work and his ongoing defense of the Martian canal theory, took a toll on Lowell's health. He suffered from exhaustion and nervous complaints, yet he refused to abandon his quest. Planet X had become an obsession, a mathematical certainty that simply had to exist, waiting to be found by whoever had the patience and skill to locate it. Tragically, Percival Lowell died on November 12, 1916, without finding the planet he had sought for more than a decade. He was 61 years old, worn out by his labours and his controversies. In his will, he left provisions for the continued operation of the Lowell Observatory and expressed his hope that the search for Planet X would continue. But the search did not continue immediately. Lowell's death was followed by a bitter legal dispute over his estate, initiated by his widow Constance, who contested the provisions he'd made for the observatory. The lawsuit dragged on for years, consuming resources that might otherwise have funded astronomical research. The search for Planet X was suspended, the photographic plates gathering dust while lawyers argued over money. It was not until 1929 that the Lowell Observatory was finally able to resume the hunt in earnest. By then, new technology had become available that would make the search more efficient. A new telescope had been acquired, specifically designed for the wide-field photography needed to survey large areas of sky, and a new astronomer had been hired, a young man from Kansas with no formal training, but an extraordinary talent for careful, patient observation. The stage was set for one of the most remarkable discoveries in the history of astronomy. Percival Lowell's dream was about to be realized, though not quite in the way he had imagined. The planet that would be found was nothing like the massive world Lowell had predicted. It was small, icy, and strange, a world that would challenge our understanding of the solar system and our definitions of what a planet truly is. As we shall see, the discovery of Pluto was as much a product of luck as of skill, a cosmic coincidence that placed a tiny world almost exactly where Lowell's flawed calculations had predicted a giant should be. But before we can appreciate the serendipity of that discovery, we must first meet the remarkable young man who made it, a farm boy from Kansas who would change our understanding of the solar system forever. Section 3, Clyde Tombaugh, the farm boy who found a world. In the small farming community of Streator, Illinois, on February 4th, 1906, Clyde William Tombaugh was born into a world that seemed to offer few opportunities for astronomical greatness. His family were farmers, hard-working people who coaxed crops from the soil and lived by the rhythms of planting and harvest. Young Clyde grew up knowing the value of patience and persistence, virtues that would serve him well in the years to come. The Tombaugh family moved to a farm near Baudette, Kansas, when Clyde was a teenager, seeking better land and new opportunities. Kansas in the 1920s was a place of vast horizons and enormous skies, where the Milky Way blazed overhead on clear nights, and the stars seemed close enough to touch. It was here, under those prairie skies, that Clyde Tombaugh fell in love with astronomy. His introduction to the cosmos came through his uncle Lee, who owned a small telescope and shared his nephew's curiosity about the heavens. Clyde was immediately captivated by what he saw through that modest instrument. The craters of the moon, the rings of Saturn, the moons of Jupiter. He began reading everything he could find about astronomy, teaching himself the mathematics and physics that would allow him to understand what he was observing. But Clyde Tombaugh was not content merely to observe the heavens. He wanted to see more, to push beyond the limits of his uncle's small telescope. And so, with characteristic determination, he decided to build his own. The construction of a telescope is a demanding task requiring precision optics and careful engineering. Tombaugh had no formal training in either field, but he had something perhaps more valuable, an intuitive understanding of how things worked and an absolute refusal to accept failure. He ground his own mirrors by hand, a process that required countless hours of patient polishing to achieve the precise curvature needed to focus starlight. His first attempts were failures, the mirrors flawed in ways that rendered them useless. But Tombaugh learned from each mistake, refining his technique, developing an ever more delicate touch. Eventually, he succeeded in creating a 9-inch reflecting telescope of remarkable quality, an instrument that would have been the pride of many professional observatories. With his homemade telescope, Tombaugh began making detailed observations of the planets, particularly Mars and Jupiter. He made careful drawings of what he saw, documenting the changing features of these distant worlds with an artist's eye and a scientist's precision. These drawings were good, remarkably good, for an amateur working with homemade equipment on a Kansas farm. In 1928, Tombaugh made a decision that would change his life. He gathered up his best drawings of Mars and Jupiter and mailed them to the Lowell Observatory in Flagstaff, Arizona. He was not applying for a job. He did not even know if the observatory had any positions available. He simply wanted the opinion of professional astronomers on his work. Perhaps they could offer suggestions for improvement. Perhaps they might be willing to correspond with a curious young farmer who loved the stars. The timing of Tombaugh's letter was extraordinary. The Lowell Observatory had just resolved its legal difficulties and was preparing to resume the search for Planet X. They needed someone to operate the new photographic telescope that had been acquired for the search, someone with patience, dedication, and sharp eyes. The professional astronomers on staff were occupied with other research. They needed an assistant who could handle the tedious work of photographing the sky night after night and comparing the resulting plates. When Tombaugh's drawings arrived at the observatory, they caused an immediate sensation. The quality was exceptional, demonstrating not only technical skill, but also the kind of careful, patient observation that the Planet X search would require. Here was someone who could clearly see fine detail and record it accurately, exactly the skills needed for the work at hand. Vesto Melvin Slifer, the director of the Lowell Observatory, wrote back to Tombaugh with an unexpected offer. Would he be interested in coming to Flagstaff to assist with a special photographic project? The salary was modest, but the opportunity was extraordinary. Tombaugh did not hesitate. In January 1929, he boarded a train for Arizona, leaving behind the wheat fields of Kansas for the pine forests of Flagstaff. Tombaugh arrived at the Lowell Observatory on January 15, 1929, just a few weeks before his 23rd birthday. He had never been to Arizona before, had never worked at a professional observatory, had never even taken a college course in astronomy. But he possessed something that no amount of formal education could provide, an absolute dedication to careful, precise work, and an ability to maintain focus through endless hours of tedious observation. The telescope Tombaugh would use for the Planet X search was a 13-inch astrograph, a specialized instrument designed to photograph wide areas of sky with minimal distortion. Each photograph, or plate, captured a region of sky about 14 by 17 degrees, containing hundreds of thousands of stars. The search strategy was straightforward. Photograph the same region of sky on different nights, then compare the photographs looking for any object that had moved. The comparison was done using a blink comparator, a device that allowed the observer to rapidly switch between two photographs of the same star field. Stars, being essentially infinitely distant, would appear in exactly the same position on both plates, but a planet, being much closer, would have moved slightly between exposures, causing it to appear to jump back and forth when the plates were blinked. The work was exhausting. Tombaugh would spend his nights at the telescope, guiding long exposures through the cold Arizona darkness. Then he would spend his days at the blink comparator, systematically scanning each plate, checking every point of light for motion. A single plate might contain 300,000 stars or more, each one needing to be examined. The strain on the eyes was tremendous, and the mental focus required was absolute. Tombaugh threw himself into the work with characteristic intensity. He developed techniques to improve the efficiency of the search, learned to recognize the various artifacts and defects that could mimic planetary motion, and maintained meticulous records of every plate examined. He was searching for a needle in a cosmic haystack, but he never doubted that the needle was there to be found. The search focused on the region of sky near the ecliptic, the plane in which the planets orbit the Sun. Lowell's calculations had predicted that Planet X would be found in the constellation Gemini, and this is where Tombaugh concentrated his efforts. Night after night, he photographed Gemini and the surrounding constellations. Day after day, he blinked the resulting plates, searching for that telltale jump that would reveal a new world. Months passed without success. Summer came, and Gemini sank below the horizon, hidden in the glare of the sun. Tombaugh used the time to examine plates of other regions, to refine his techniques, to prepare for the return of Gemini to the evening sky. When autumn arrived and the constellation rose again, in the east he resumed the search with renewed determination. The breakthrough came on February 18, 1930. Tombaugh was examining plates taken on January 23rd and January 29th, blinking back and forth between them, when he noticed something unusual. A faint point of light, barely visible among the dense star fields of Gemini, was jumping back and forth. It had moved, just as a planet should move. Tombaugh's heart raced, but he forced himself to remain calm. He had seen false alarms before, defects in the photographic emulsion that mimicked planetary motion. He checked the position carefully, comparing it to a third plate taken on January 21st. The object appeared on all three plates in exactly the positions expected for a trans-Neptunian planet. This was no defect. This was real. Even then, Tombaugh did not rush to announce his discovery. He spent another hour examining the plates, convincing himself that he had not made a mistake. Only when he was absolutely certain did he walk down the hall to the office of Carl Lamplund, one of the senior astronomers, and speak the words that would change history. "I have found your planet X." The announcement was delayed for several weeks, while the observatory confirmed the discovery and calculated a preliminary orbit. On March 13, 1930, the 75th anniversary of Percival Lowell's birth and the 149th anniversary of William Herschel's discovery of Uranus, the Lowell Observatory announced to the world that a new planet had been found. The news was a sensation. Newspapers around the world carried the story on their front pages. Telegrams of congratulation poured into Flagstaff from astronomers and ordinary citizens alike. Clyde Tombaugh, the farm boy from Kansas, who had never attended college, had discovered a new world. But even in those first heady days, there were hints that the new planet was not quite what Lowell had predicted. It was faint, much fainter than expected for a world 7 times the mass of Earth. Early estimates suggested it might be smaller than anticipated, perhaps comparable in size to Earth rather than the giant Lowell had envisioned. These discrepancies would only grow more pronounced in the years to come, but for the moment they were overshadowed by the joy of discovery. Tombaugh's achievement was all the more remarkable for the circumstances in which it occurred. He had found Pluto using equipment that, while good, was far from the best available. He had succeeded where more experienced astronomers had failed, not because he was smarter or better trained, but because he was more patient, more careful, more absolutely dedicated to the task at hand. The discovery of Pluto launched Tombaugh on a distinguished astronomical career. He would eventually earn his bachelor's and master's degrees, teach at New Mexico State University, and continue searching the skies for decades. He discovered hundreds of asteroids, a comet, and numerous star clusters and galaxy clusters, but he would always be remembered primarily as the man who found Pluto, the last planet discovered in our solar system. Clyde Tombaugh lived long enough to see the beginning of the space age, to watch as humanity sent probes to the planets he had studied through his telescopes. He died on January 17, 1997, at the age of 90, still passionate about astronomy, still curious about the cosmos. When the New Horizons spacecraft was launched toward Pluto in 2006, it carried a small container of Tombaugh's ashes, ensuring that the man who discovered Pluto would be the first human to visit it. Section 4. Naming the 9th planet. Mythology meets discovery. With the discovery announced and the astronomical community buzzing with excitement, attention turned to a question that might seem trivial but was actually of considerable importance. What should the new planet be called? The naming of celestial bodies is governed by tradition and convention, and the name chosen for Lowell's Planet X would echo through history, shaping how generations would think about this distant world. The tradition for naming planets stretches back to antiquity. The 5 planets visible to the naked eye, Mercury, Venus, Mars, Jupiter and Saturn, were named by the ancient Romans after gods in their pantheon. When William Herschel discovered Uranus in 1781, he initially wanted to name it Georgium Sidus, George's star, after King George III of England. This suggestion was not well received outside Britain, and eventually the astronomical community settled on Uranus, the Greek god of the sky and father of Saturn in mythology, maintaining the tradition of naming planets after classical deities. Neptune, discovered in 1846, was named after the Roman god of the sea, a fitting choice for a blue-tinged world in the cold outer reaches of the solar system. The name was suggested by Leverrier, who had calculated Neptune's position, and was quickly accepted by the astronomical community. For the new planet discovered at Lowell Observatory, the naming process was more complicated. Suggestions poured in from around the world, some serious, some whimsical, some self-serving. Percival Lowell's widow, Constance, suggested that the planet be named Percival or Lowell, honouring her late husband who had predicted its existence and initiated the search. Others suggested Cronus, the Greek equivalent of Saturn, or Minerva, the Roman goddess of wisdom. The name that would ultimately be chosen came from an unexpected source. An 11-year-old girl in Oxford, England, named Venetia Burney. On the morning of March 14, 1930, the day after the discovery was announced, Venetia was having breakfast with her grandfather, Falconer Madan, a retired librarian from the Bodleian Library at Oxford University. Marden was reading the newspaper account of the discovery aloud when Venetia made a suggestion that would immortalise her in astronomical history. "I think Pluto would be a good name for it," she said. Pluto was the Roman god of the underworld, the dark realm beneath the earth where the souls of the dead resided. It was a fitting name for a world so distant from the sun, perpetually shrouded in darkness and cold. Venetia, who had recently been studying classical mythology in school, recognised immediately that the existing planets were named after Roman gods, and that the new planet deserved a name from the same tradition. Falconer Marden was impressed by his granddaughter's suggestion. He passed it along to Herbert Hall Turner, a professor of astronomy at Oxford, who in turn cabled it to colleagues at the Lowell Observatory. The suggestion arrived in Flagstaff, along with hundreds of others, but it stood out for its classical appropriateness and its symbolic resonance. The staff at Lowell Observatory voted on the various suggestions, and Pluto emerged as the clear favourite. The name had multiple advantages beyond its mythological appropriateness. The first 2 letters, P and L, were the initials of Percival Lowell, providing a subtle tribute to the man whose vision had led to the search. The name was also associated with darkness and distance, qualities that perfectly described the cold, remote world that Tombaugh had found. On May 1st, 1930, the name Pluto was officially announced. The astronomical symbol chosen for the new planet was a monogram combining the letters P and L, another nod to Percival Lowell. The symbol resembled a trident, which some saw as appropriate for a world in the outer darkness of the solar system. Venetia Burney received £5 as a reward for her suggestion, a substantial sum for a child, in 1930. She went on to live a long and fulfilling life, becoming a teacher of economics and mathematics. She rarely spoke publicly about her role in naming Pluto, but she followed news of the distant world with quiet interest throughout her life. When the New Horizons mission was being planned, she expressed her hope that she would live to see the spacecraft reach Pluto. Sadly, she died in April 2009, 6 years before the flyby, but her contribution to astronomical history remains secure. The name Pluto quickly entered popular culture. Within months of the announcement, Walt Disney introduced a cartoon character named Pluto, a loyal dog who would become one of the most beloved figures in animation history. Disney always maintained that the dog was named after the planet, though some historians have questioned whether the timing was quite so straightforward. Regardless of the exact inspiration, the coincidence cemented the name Pluto in the public consciousness, associating it with both cosmic mystery and cartoon whimsy. The mythological associations of the name Pluto added layers of meaning to the distant world. In Roman mythology, Pluto was the ruler of the underworld, a realm of shadows and spirits, of endings and transformations. He was the brother of Jupiter and Neptune, which gave the name a pleasing symmetry with the other outer planets. He was also associated with wealth, since precious metals and gems came from beneath the earth, his domain. The Greeks knew this god as Hades, a name that carried darker connotations. Hades was feared rather than worshipped, his name spoken reluctantly if at all. The Romans softened this image somewhat, emphasizing Pluto's role as a god of hidden riches rather than a fearsome lord of the dead. But the association with death and darkness remained, giving the name Pluto an air of mystery and foreboding that seemed appropriate for a world at the edge of the known solar system. The naming of Pluto also reflects the international nature of astronomical discovery. An American observatory, founded by a Boston aristocrat, hired a Kansas farm boy who found a world that was named by a British schoolgirl using Roman mythology. The story crosses boundaries of class, nationality, and age, demonstrating that contributions to human knowledge can come from the most unexpected sources. In the decades that followed, the name Pluto became so firmly established that it seemed impossible to imagine the world being called anything else. When astronomers discovered Pluto's moons, they named them after figures from the same mythological tradition. Charon, the ferryman who carried souls across the river Styx to the underworld; Nyx, the goddess of night; Hydra, the many-headed serpent; Kerberos, the three-headed dog who guarded the gates of Hades; and Styx, the river that formed the boundary between the world of the living and the realm of the dead. This consistent mythological naming created a coherent narrative around Pluto and its satellites, a story of darkness and passage, of boundaries and transformations. The names invited us to think of Pluto not merely as a ball of ice and rock, but as a place with meaning, a destination with resonance. When New Horizons finally arrived at Pluto in 2015, the features discovered on its surface were named according to themes of exploration and the underworld, continuing the tradition that Venetia Burney had begun 85 years earlier. The story of how Pluto got its name reminds us that science is a human endeavour, shaped by culture and history as much as by observation and calculation. The name we give to a thing affects how we think about it, how we relate to it, how we remember it. Pluto, with its mythological weight and its cultural associations, became more than just another point of light in the sky. It became a character in the human story of cosmic exploration, a destination for dreams and aspirations, a symbol of the unknown waiting to be discovered. Section 5. Decades of Mystery. Pluto in the pre-space age. For more than half a century after its discovery, Pluto remained one of the most mysterious objects in the solar system. It was too small and too distant to reveal its secrets easily, appearing in even the largest telescopes as little more than a faint point of light. Astronomers could track its motion, calculate its orbit, and make educated guesses about its nature. But direct observation of surface features was impossible with the technology of the time. The first challenge was simply determining Pluto's size. When Tombaugh discovered it, many astronomers assumed it must be a substantial world, perhaps comparable to Earth in mass, since Lowell's calculations had predicted a planet large enough to perturb the orbit of Uranus. But Pluto's faintness suggested otherwise. A planet the size of Earth at Pluto's distance should have been much brighter than what Tombaugh observed. The question of Pluto's mass was equally vexing. If Pluto were truly responsible for the perturbations in Uranus's orbit, it would need to be quite massive, perhaps several times the mass of Earth. But its small apparent size suggested something far less substantial. This contradiction puzzled astronomers for decades, creating a mystery that would not be fully resolved until the late 20th century. Throughout the 1930s and 1940s, astronomers continued to refine their estimates of Pluto's properties. Gerard Kuiper, a Dutch-American astronomer who would later have an entire region of the solar system named after him, made careful observations of Pluto in 1950 and estimated its diameter at approximately 5,900 kilometers, roughly half the size of Earth. This estimate, while still too large, represented a significant improvement over earlier guesses and began to establish that Pluto was indeed a small world. Kuiper also made the first attempts to determine Pluto's surface composition through spectroscopy, the analysis of light reflected from the planet's surface. His observations suggested that Pluto might be covered in frozen methane, a finding that would be confirmed decades later. This was an important clue about Pluto's nature, indicating that it was a frigid world where temperatures were cold enough for gases like methane to exist as solid ice. The orbit of Pluto itself presented fascinating puzzles. Unlike the other planets, which travel around the Sun in nearly circular paths close to the same plane, Pluto's orbit is highly elliptical and significantly tilted. Its orbital eccentricity of 0.25 means that its distance from the Sun varies enormously over the course of its 248-year journey around our star. At its closest approach to the Sun, called perihelion, Pluto comes within 4.4 billion kilometers of our star. At its most distant point, aphelion, it recedes to 7.4 billion kilometers away. This eccentric orbit has a remarkable consequence. For roughly 20 years out of every 248-year orbital period, Pluto is actually closer to the Sun than Neptune. This occurred most recently between 1979 and 1999, during which time Pluto was technically the 8th planet from the Sun, rather than the 9th. This orbital peculiarity led some astronomers to wonder whether Pluto might be a former moon of Neptune that had somehow escaped into its own orbit, though this theory was eventually discarded as dynamically implausible. The tilt of Pluto's orbit is equally unusual. While most planets orbit within a few degrees of the ecliptic plane, Pluto's orbit is inclined by more than 17 degrees. This means that Pluto spends much of its time well above or below the plane in which the other planets travel, adding to its sense of being an outsider in the solar system family. Astronomers in the mid-20th century also began to notice that Pluto's brightness varied in a regular pattern, growing slightly brighter and dimmer over a period of about 6.4 Earth days. This variation suggested that Pluto was rotating on its axis with this period, and that its surface was not uniform in reflectivity. Some regions were brighter than others, and as the planet rotated, these different regions came into view, causing the observed brightness changes. The 6.4-day rotation period was unusually slow for a small body. Most asteroids and small moons rotate much faster, completing a full turn in just hours. Pluto's leisurely spin hinted at some past event that had slowed its rotation, perhaps a collision with another object or gravitational interactions with an unseen companion. This hint would prove prophetic, though the full explanation would not come until 1978. Throughout these decades of observation, Pluto remained stubbornly enigmatic. It was too far away for detailed study, too small to reveal surface features, too mysterious to fit neatly into existing categories. Some astronomers began to question whether Pluto deserved to be called a planet at all, noting its small size, unusual orbit, and apparent compositional differences from the gas giants that dominated the outer solar system. But these doubts remained largely academic. Pluto had been announced as a planet, had been accepted as a planet, and had been taught as a planet to generations of schoolchildren. Changing its status would require not just scientific justification, but a willingness to overturn decades of tradition. For the time being, Pluto's place in the planetary family seemed secure. The space age dawned in 1957 with the launch of Sputnik, and over the following decades, spacecraft visited every planet in the solar system except Pluto. Mariner probes flew past Mercury, Venus, and Mars. Pioneer and Voyager spacecraft explored Jupiter, Saturn, Uranus, and Neptune. These missions transformed our understanding of the solar system, revealing worlds of astonishing diversity and complexity. But Pluto remained beyond reach. Its immense distance made it a challenging target for spacecraft, and its small size meant that a mission would need to approach very close to gather meaningful data. Various Pluto missions were proposed over the years, but none were approved. Budgetary constraints, technical challenges, and competing priorities kept Pluto at the bottom of the exploration agenda. As the 20th century drew to a close, Pluto remained the only planet never visited by a spacecraft, a distinction that seemed increasingly anomalous as our knowledge of the other planets grew ever more detailed. The contrast between what we knew about worlds like Mars and Jupiter and what we knew about Pluto was stark and frustrating. Pluto was the last frontier, the final unexplored planet, a world that existed more in imagination than in scientific understanding. This situation would begin to change dramatically in 1978 with a discovery that would transform our understanding of Pluto and set the stage for the debates and explorations to come. But before we explore that discovery, let us pause to appreciate the decades of patient observation that preceded it, the years of squinting at faint points of light, of refining estimates and revising theories, of wondering what secrets that distant world might hold. The astronomers who studied Pluto in the pre-space age were working at the very limits of their technology. They could not send probes to gather data directly. They could not resolve surface features through their telescopes. They could only watch, measure, calculate, and imagine. Their work laid the foundation for everything that followed, establishing the basic parameters of Pluto's orbit, rotation, and composition that would guide future investigations. These decades of mystery also established Pluto's place in popular culture. The distant planet became a symbol of the unknown, the unreachable, the edge of the solar system. Science fiction writers set stories on its frozen surface, imagining what strange landscapes and alien life forms might exist there. Artists depicted Pluto as a world of eternal twilight, where the sun appeared as merely a bright star in an ink-black sky. The mystery of Pluto captured something essential about the human relationship with the cosmos. We are creatures who yearn to know, to understand, to explore. When confronted with the unknown, we do not turn away but lean in, straining to see what lies beyond the limits of our vision. Pluto, for all its distance and obscurity, represented that yearning, that refusal to accept that some things must remain forever beyond our grasp. Section 6. The discovery of Charon and Pluto's true nature. The year 1978 brought a discovery that would fundamentally change our understanding of Pluto. On the night of June 22nd, astronomer James Christie was examining photographic plates of Pluto taken at the United States Naval Observatory in Flagstaff, Arizona, not far from where Clyde Tombaugh had made his historic discovery nearly 50 years earlier. Christie noticed something peculiar about the images. Pluto appeared to have a bump, a slight elongation that should not have been there. At first, Christie suspected the elongation was an artifact, perhaps caused by a flaw in the photographic plate or atmospheric distortion during the exposure. But when he examined other plates taken on different nights, he found the same elongation, always present but appearing at different positions around Pluto. The bump was moving, circling Pluto in a regular pattern that could only mean one thing. Pluto had a moon. The discovery was confirmed through careful analysis of the photographic record. The moon, which Christie named Charon after the mythological ferryman who transported souls across the river Styx to the underworld, orbited Pluto at a distance of only about 19,600 kilometers, completing one orbit every 6,387 days. This orbital period was identical to Pluto's rotation period, meaning that Charon always showed the same face to Pluto and Pluto always showed the same face to Charon, a configuration known as mutual tidal locking. The name Charon was particularly fitting not only for its mythological appropriateness, but also for a personal reason. Christie's wife was named Charlene, and her nickname was Char. The first syllable of Charon, pronounced differently in astronomical usage than in classical mythology, honoured both the ancient ferryman and the astronomer's beloved spouse. The discovery of Charon was momentous for several reasons. Most importantly, it finally allowed astronomers to determine Pluto's mass with precision. When two objects orbit each other, their orbital characteristics depend on their combined mass. By measuring how fast Charon orbited Pluto and at what distance, astronomers could calculate the total mass of the Pluto-Charon system. The result was shocking. Pluto's mass turned out to be only about 0.2% of Earth's mass, far smaller than anyone had expected. This was not a world capable of perturbing the orbit of Uranus. The gravitational influence of something so small would be negligible at such distances. The perturbations that Percival Lowell had calculated, the very perturbations that had motivated the search for Planet X, could not possibly have been caused by Pluto. This revelation raised an obvious question. If Pluto was not responsible for the perturbations in Uranus's orbit, why had Tombaugh found it almost exactly where Lowell's calculations predicted? The answer, it turned out, was pure coincidence. Lowell's calculations were based on flawed data and incorrect assumptions. The perturbations he thought he had detected were largely illusory, artifacts of measurement error rather than evidence of an unseen planet. Tombaugh had found Pluto not because Lowell's mathematics were correct, but because he had searched a large area of sky with extraordinary thoroughness. Pluto happened to be there, but it had nothing to do with the wobbles in Uranus's orbit. This coincidence is one of the most remarkable in the history of astronomy. Tombaugh found a real object in almost exactly the location where Lowell had predicted a very different object should exist. The predicted planet and the actual discovery had almost nothing in common except their approximate position in the sky. It was as if someone had predicted the existence of an elephant in a particular room, and upon searching, found a mouse sitting in the expected spot. The prediction was wrong in every detail except location. The discovery of Charon also revealed that Pluto was even smaller than previous estimates had suggested. With the mass now known, and with improved measurements of Pluto's brightness, astronomers could calculate that Pluto was only about 2,300 kilometers in diameter, smaller than Earth's moon, smaller even than several other moons in the solar system. Pluto was not just small for a planet, it was tiny. Charon itself proved to be surprisingly large relative to Pluto, with a diameter of approximately 12 kilometers. Charon is more than half the size of Pluto, making the Pluto-Charon system unique in the solar system. No other planet has a moon so large in proportion to itself. Some astronomers began referring to Pluto and Charon as a double planet, or binary system, rather than a planet and moon, recognizing the unusual nature of their relationship. The center of mass of the Pluto-Charon system, the point around which both objects actually orbit, lies outside of Pluto itself, in the space between the two bodies. This is unlike any other planet-moon system, where the center of mass lies within the larger body. Earth and its moon, for example, orbit a common center of mass located about 1,700 kilometers below Earth's surface. For Pluto and Charon, the equivalent point floats in empty space, a testament to how closely matched the two objects are in mass. The mutual tidal locking of Pluto and Charon means that an observer standing on Pluto would see Charon hanging motionless in the sky, never rising or setting, always occupying the same position relative to the horizon. From some locations on Pluto, Charon would never be visible at all, hidden forever below the horizon. From other locations it would dominate the sky, appearing several times larger than the full moon appears from Earth. The years following the discovery of Charon brought additional insights into Pluto's nature. In the late 1980s, a fortuitous alignment allowed astronomers to observe Pluto and Charon passing in front of each other as seen from Earth. These mutual eclipse events, which occur only twice during Pluto's 248-year orbit, provided valuable information about the sizes, shapes, and surface properties of both objects. During these eclipses, astronomers measured how the combined brightness of the Pluto-Charon system changed as one object blocked light from the other. By carefully analysing these brightness variations, they could map the distribution of light and dark regions on both surfaces. The results revealed that Pluto had a varied surface, with bright polar caps and darker equatorial regions, while Charon appeared more uniformly grey. Spectroscopic observations during this period confirmed that Pluto's surface was covered with frozen nitrogen, methane, and carbon monoxide, ices that would be gases at Earth's temperatures but were frozen solid in Pluto's extreme cold. Charon's surface, by contrast, appeared to be dominated by water ice, suggesting a different composition and perhaps a different origin. The discovery of Charon and the subsequent observations of the Pluto-Charon system raised profound questions about Pluto's place in the solar system. Here was a world that was smaller than many moons, that had a companion nearly as large as itself, that was covered in exotic ices, and that travelled in a highly unusual orbit. Was this really a planet in the same sense as Jupiter or Earth? Or was it something else entirely? A different kind of object that had been misclassified due to historical accidents? These questions would simmer for decades, occasionally bubbling up into public debate before subsiding again. The answers would eventually come, but they would prove controversial, challenging not just our scientific understanding, but our emotional attachment to the small distant world that had captured our imagination for so long. Section 7. The Great Debate. Pluto's planetary status. The question of what constitutes a planet might seem straightforward, but it has occupied astronomers and philosophers for centuries. The word planet comes from the Greek word for wanderer, reflecting the ancient observation that certain bright objects in the night sky moved against the background of fixed stars. The ancients counted 7 planets: the Sun, the Moon, Mercury, Venus, Mars, Jupiter, and Saturn, all visible to the naked eye and all appearing to wander through the zodiac. Our modern understanding of planets emerged gradually over centuries of observation and theorizing. Copernicus placed the Sun at the center of the solar system, demoting it from planetary status while elevating Earth to that category. The Moon was recognized as a satellite of Earth rather than a planet in its own right. Uranus and Neptune were discovered, extending the planetary family to the outer reaches of the solar system. Throughout this evolution, the definition of planets remained somewhat informal. Planets were large objects that orbited the Sun, distinct from the smaller asteroids and comets that also populated the solar system. The distinction seemed clear enough. Planets were big, asteroids were small, and everyone could tell the difference. Pluto complicated this picture from the very beginning. It was smaller than expected, travelled in an unusual orbit, and seemed compositionally different from its planetary neighbours. But for decades these anomalies were treated as curiosities rather than challenges to Pluto's planetary status. Pluto was a planet because it had been declared a planet, and that seemed to settle the matter. The situation began to change in the 1990s with the discovery of the Kuiper Belt, a vast region of icy objects beyond Neptune that had been theorized for decades, but not directly observed until 1992. The first Kuiper Belt object, designated 1992 QB1, was discovered by astronomers David Jewett and Jane Liu using the University of Hawaii's telescope on Mauna Kea. It was a small icy body orbiting the Sun beyond Neptune, and it was just the first of thousands that would eventually be found. The discovery of the Kuiper Belt transformed our understanding of the outer solar system. Rather than being a lonely outpost at the edge of planetary space, Pluto appeared to be the largest member of a vast population of similar objects. The Kuiper Belt contained countless icy bodies, ranging from tiny fragments to substantial worlds hundreds of kilometres across. Pluto was not unique, it was simply the first and largest of its kind to be discovered. This realization forced astronomers to confront an uncomfortable question. If Pluto was a planet, were all the other Kuiper Belt objects planets too? And if not, what made Pluto different? The traditional answer that Pluto was simply larger than the others became increasingly difficult to maintain as larger and larger Kuiper Belt objects were discovered. The crisis came to a head in 2005 with the announcement of several objects that rivaled or exceeded Pluto in size. Most significantly, astronomer Mike Brown and his colleagues at the California Institute of Technology discovered an object initially designated 2003 UB313, which appeared to be slightly larger than Pluto. This object, eventually named Eris after the Greek goddess of discord, forced the astronomical community to make a decision. Either Eris and similar objects would have to be recognized as planets, potentially adding dozens of new planets to the solar system, or Pluto would have to be reclassified. The International Astronomical Union, the organization responsible for official astronomical nomenclature, convened a meeting in Prague in August 2006 to address the issue. The debate was intense and sometimes acrimonious, with astronomers holding strong opinions on both sides. Some argued that tradition should prevail and that Pluto should remain a planet regardless of what other objects might be discovered. Others insisted that scientific consistency required a clear definition that would apply equally to all objects. After days of discussion, the IAU voted on August 24, 2006 to adopt a new definition of planet. According to this definition, a planet must meet 3 criteria. It must orbit the Sun, it must have sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a nearly round shape, and it must have cleared the neighbourhood around its orbit. Pluto met the first 2 criteria easily. It orbits the Sun, and it is massive enough to be round. But it failed the 3rd criterion. Pluto has not cleared its orbital neighbourhood. It shares the Kuiper Belt with thousands of other objects, and is gravitationally influenced by Neptune. Under the new definition, Pluto was not a planet. The IAU created a new category for objects like Pluto, dwarf planets. These are objects that orbit the Sun, are massive enough to be round, but have not cleared their orbital neighbourhoods. Pluto became the prototype of this new category, joined by Eris, Ceres, the largest object in the asteroid belt, and eventually several other Kuiper belt objects. The reaction to Pluto's reclassification was immediate and emotional. Many people felt that something precious had been taken from them, that a beloved member of the planetary family had been unfairly demoted. Protests erupted, petitions circulated, and state legislatures passed resolutions declaring that Pluto would always be a planet within their borders. The intensity of feeling surprised many astronomers who had approached the reclassification as a matter of scientific precision rather than cultural significance. The debate over Pluto's status continues to this day. Many planetary scientists, including those who have studied Pluto most closely, reject the IAU definition and continue to consider Pluto a planet. They argue that the clearing criterion is arbitrary and poorly defined, that it would disqualify Earth if our planet were placed in the Kuiper belt, and that the most important characteristic of a planet is its intrinsic properties rather than its orbital environment. Alan Stern, the principal investigator of the New Horizons mission to Pluto, has been particularly vocal in his criticism of the IAU decision. He argues that the definition was adopted by a small minority of astronomers, that the vote was procedurally flawed, and that the resulting classification makes little scientific sense. For Stern and many others, Pluto is and always will be a planet. The controversy over Pluto's status has had unexpected benefits for science education. The debate has sparked public interest in planetary science and has provided teachers with an opportunity to discuss how scientific knowledge evolves. Students learn that science is not a collection of fixed facts, but a dynamic process of observation, hypothesis, and revision. Pluto's reclassification demonstrates that even fundamental categories can change as our understanding grows. The debate has also highlighted the difference between scientific and cultural definitions. From a scientific perspective, the question of whether Pluto is a planet is a matter of classification, of deciding which objects belong in which categories. From a cultural perspective, Pluto's status is about meaning and identity, about our relationship with the cosmos and our place within it. These two perspectives do not always align, and the Pluto controversy has made that tension visible. Whatever one thinks about Pluto's official classification, there is no denying that it remains one of the most fascinating objects in the solar system. Its complex surface, its family of moons, its tenuous atmosphere, and its dynamic geology make it a world worthy of study regardless of what label we attach to it. The New Horizons mission would soon reveal just how remarkable Pluto truly is, providing images and data that would captivate the world and reignite our fascination with this distant, icy realm. Section 8. The Kuiper Belt, Pluto's true neighbourhood. To truly understand Pluto, we must understand the cosmic neighbourhood in which it resides. The Kuiper Belt is one of the most significant discoveries in modern planetary science, a vast reservoir of icy objects that extends from the orbit of Neptune outward to perhaps 50 astronomical units from the Sun. This region, named after Dutch-American astronomer Gerard Kuiper, who predicted its existence in 1951, contains millions of frozen worlds, remnants from the formation of the solar system that have remained largely unchanged for billions of years. Gerard Kuiper was one of the most influential planetary scientists of the 20th century. Born in the Netherlands in 1905, he emigrated to the United States and became a pioneer in the study of the solar system. His contributions ranged from discovering moons of Uranus and Neptune to making the first spectroscopic detection of methane in Titan's atmosphere. But perhaps his most lasting legacy is the belt of icy objects that bears his name. Kuiper theorized that the outer solar system should contain a disk of debris left over from the formation of the planets. This debris, he reasoned, would consist primarily of ices, frozen water, methane, ammonia, and other volatile compounds that could only exist as solids in the frigid temperatures beyond Neptune. The objects in this disk would be too small and too faint to detect with the telescopes of his era, but they should be there, waiting to be discovered. For decades, the Kuiper belt remained theoretical. Astronomers searched for evidence of its existence but found nothing. Some began to doubt whether the belt existed at all, suggesting that perhaps the outer solar system was empty, swept clean by some unknown process. The breakthrough came in 1992 when astronomers David Jewitt and Jane Liu discovered the first confirmed Kuiper belt object beyond Pluto. Designated 1992 QB1, this small icy body was about 200 kilometers in diameter and orbited the Sun at a distance of about 44 astronomical units. It was the first direct evidence that Kuiper's prediction was correct, that the outer solar system was indeed populated with icy remnants from the solar system's formation. The discovery of 1992 QB1 opened the floodgates. Over the following years, astronomers discovered hundreds, then thousands of Kuiper belt objects. These objects ranged in size from small fragments just a few kilometers across to substantial worlds hundreds of kilometers in diameter. The Kuiper belt was not just real, it was vast, containing far more objects than the asteroid belt between Mars and Jupiter. The Kuiper belt objects, often abbreviated as KBOs, fall into several distinct categories based on their orbital characteristics. Classical KBOs, sometimes called cubewanos, after the prototype 1992 QB1, orbit the Sun in relatively circular paths between about 42 and 48 astronomical units. These objects have stable orbits that have remained largely unchanged since the formation of the solar system. Resonant KBOs have orbits that are locked in gravitational resonance with Neptune. The most famous of these are the Plutinos, objects that share Pluto's 3.2 resonance with Neptune, completing 2 orbits of the Sun for every 3 orbits Neptune completes. This resonance protects these objects from close encounters with Neptune, allowing them to survive in orbits that would otherwise be unstable. Scattered disk objects have highly elliptical orbits that can take them far beyond the classical Kuiper belt. These objects were probably scattered outward by gravitational encounters with Neptune during the early history of the solar system. Some scattered disk objects have orbits that extend hundreds of astronomical units from the Sun, venturing into the cold darkness of the outer solar system. The discovery of the Kuiper belt transformed our understanding of Pluto. Rather than being a unique object at the edge of the planetary system, Pluto appeared to be the largest member of a vast population of similar bodies. Its composition, orbit, and size all fit the pattern of Kuiper belt objects. Pluto was not an anomalous planet, but a typical, if unusually large, member of the Kuiper belt. This realization had profound implications for our understanding of the solar system's history. The Kuiper belt preserves material from the earliest days of the solar system, icy building blocks that never coalesced into larger planets. By studying these objects, astronomers can learn about the conditions that prevailed when the Sun and planets were forming over 4.5 billion years ago. The Kuiper belt also provides clues about the early migration of the giant planets. Computer simulations suggest that Neptune originally formed much closer to the Sun than its current position and migrated outward over millions of years. As Neptune moved, its gravity scattered countless small objects, some inward toward the Sun, where they became comets, others outward into the scattered disk. The current structure of the Kuiper belt bears the imprint of this ancient migration, a fossil record of the solar system's turbulent youth. Among the most significant Kuiper belt discoveries was Eris, found in 2005 by Mike Brown and his team at Caltech. Eris was initially thought to be larger than Pluto, though subsequent measurements by the New Horizons team suggest the two objects are almost exactly the same size. Eris orbits in the scattered disk, with a highly elliptical path that takes it from 38 astronomical units at its closest approach to 98 astronomical units at its most distant. Eris is accompanied by a small moon named Dysnomia, after the Greek goddess of lawlessness and the daughter of Eris. The discovery of this moon allowed astronomers to determine Eris's mass, which turned out to be about 27% greater than Pluto's, despite the two objects being similar in size. This means Eris is significantly denser than Pluto, suggesting a different internal composition, with more rock and less ice. Other notable Kuiper Belt objects include Makemake, a nearly Pluto-sized world discovered in 2005 that lacks any known moons; Haumea, an elongated object that rotates so rapidly it has been stretched into an egg shape; and Sedna, a distant object with an extremely elliptical orbit that takes it far beyond the classical Kuiper Belt. The Kuiper Belt is not the outer limit of the solar system. Beyond it lies the Oort cloud, a hypothetical spherical shell of icy objects that may extend halfway to the nearest star. The Oort cloud is thought to be the source of long-period comets, objects that plunge into the inner solar system on orbits that take thousands or millions of years to complete. No Oort cloud objects have been directly observed, but their existence is inferred from the orbits of the comets they send our way. Understanding Pluto's place in the Kuiper Belt helps us appreciate its true nature. Pluto is not a failed planet or an oddball misfit. It is the king of the Kuiper Belt, the largest and most complex member of a vast population of icy worlds. Its moons, its atmosphere, its geological activity all make sense in the context of its Kuiper Belt origins. Pluto is exactly what we should expect the largest Kuiper Belt object to be, a world of ice and rock, shaped by the same processes that formed all the other icy bodies in the outer solar system, but large enough to exhibit complexity and dynamism that smaller objects cannot achieve. The exploration of the Kuiper Belt has only just begun. New Horizons, after its encounter with Pluto, continued into the Kuiper Belt to visit another object, providing our first close-up look at a small KBO. Future missions may visit other Kuiper Belt objects, expanding our understanding of this fascinating region. And as telescope technology improves, we will undoubtedly discover many more objects in the outer solar system, each one adding to our picture of the solar system structure and history. Section 9, New Horizons, Humanity's Journey to the Edge. The dream of sending a spacecraft to Pluto began almost as soon as the space age itself. In the 1960s and 1970s, as NASA's Pioneer and Voyager probes ventured to the outer planets, scientists began to contemplate missions that would go even further to the mysterious world at the edge of the solar system. But Pluto's immense distance and small size made it a challenging target, and for decades, a Pluto mission remained just a dream. The first serious proposal for a Pluto mission came in the late 1980s, when a group of scientists began advocating for what they called the Pluto Fast Flyby. The concept was simple: send a small, lightweight spacecraft on a fast trajectory to Pluto, using Jupiter's gravity to accelerate it on its way. The spacecraft would carry a minimal instrument package, just enough to photograph Pluto and characterize its basic properties. Speed was essential because Pluto was moving away from the Sun, and its atmosphere, which depends on solar heating to remain gaseous, might freeze and collapse before a slower spacecraft could arrive. The Pluto Fast Flyby concept evolved over the years, going through multiple iterations and name changes. It became Pluto Express, then the Pluto Kuiper Express, as scientists recognized the opportunity to study not just Pluto, but other objects in the Kuiper Belt. But despite strong scientific support, the mission struggled to secure funding. NASA's budget was tight, and there were always other priorities competing for limited resources. The breakthrough came in 2001 when NASA selected the New Horizons mission for development as part of its New Frontiers program of medium-class planetary missions. The principal investigator was Alan Stern, a planetary scientist at the Southwest Research Institute, who'd been advocating for a Pluto mission for over a decade. Stern assembled a team of scientists and engineers from institutions across the country, united by their determination to finally explore the last unvisited planet. The New Horizons spacecraft was designed to be fast, light, and efficient. It weighed only about 478 kilograms at launch, roughly the mass of a grand piano. Its power came from a radioisotope thermoelectric generator, which converted heat from the decay of plutonium-238 into electricity. Solar panels would be useless at Pluto's distance, where sunlight is nearly 1,000 times weaker than on Earth. The spacecraft carried 7 scientific instruments, carefully chosen to maximize the scientific return from the brief flyby. LORRI, the long-range reconnaissance imager, was a high-resolution telescope camera capable of capturing detailed images of Pluto's surface. RALPH was a visible and infrared imaging spectrometer that would map Pluto's composition and temperature. ALICE was an ultraviolet spectrometer designed to study Pluto's atmosphere. SWAP and PEPSI would measure the solar wind and energetic particles in Pluto's environment. REX would use radio signals to probe Pluto's atmosphere and surface. And the Student Dust Counter, built by students at the University of Colorado, would measure dust particles throughout the spacecraft's journey. New Horizons launched on January 19, 2006, atop an Atlas V rocket from Cape Canaveral, Florida. It was the fastest spacecraft ever launched, leaving Earth at a velocity of over 58,000 kilometers per hour. Even at this tremendous speed, it would take more than 9 years to reach Pluto. The launch carried special significance for those who remembered Pluto's history. Aboard the spacecraft was a small container holding some of the ashes of Clyde Tombaugh, who had died in 1997. The man who discovered Pluto would be the first human to visit it. In a sense, his remains travelling further from Earth than any human material had ever gone. Also, aboard were other mementos. A piece of scaled composites Spaceship One, the first privately funded spacecraft to reach space. A CD-ROM containing the names of over 430,000 people who had signed up to have their names sent to Pluto. 2 US flags, 2 state quarters representing Florida and Maryland, where the spacecraft was launched and built, and a 1991 US postage stamp that read Pluto, not yet explored, a designation the mission would soon render obsolete. 13 months after launch, New Horizons reached Jupiter, using the giant planet's gravity to accelerate and redirect its trajectory toward Pluto. The Jupiter flyby was not just a gravitational assist, it was also an opportunity to test the spacecraft's instruments and practice the observation sequences that would be used at Pluto. New Horizons captured stunning images of Jupiter's atmosphere, moons and ring system, demonstrating that its instruments were working perfectly. The Jupiter encounter added about 14,000 kilometers per hour to New Horizons' velocity, shortening the journey to Pluto by several years. After Jupiter, the spacecraft entered a long hibernation, its systems powered down to conserve energy and reduce wear on its components. For most of the journey, New Horizons slept, waking periodically for system checks and course corrections. As New Horizons crossed the vast emptiness between Jupiter and Pluto, the science team prepared for the encounter. They developed detailed observation plans, specifying exactly when each instrument would operate and what it would observe. They practiced the flyby sequences using computer simulations, identifying potential problems and developing contingency plans. They also conducted ground-based observations of Pluto, refining their knowledge of the target and searching for any hazards that might threaten the spacecraft. One particular concern was the possibility of debris around Pluto. The discovery of Pluto's small moons, Nix and Hydra in 2005 and Kerberos and Styx in 2011 and 2012, raised the possibility that Pluto might be surrounded by a cloud of smaller particles, fragments blasted off the moons by meteorite impacts that could pose a danger to a spacecraft travelling at over 50,000 kilometers per hour. At such velocities, even a grain of sand could cause catastrophic damage. The mission team developed contingency plans in case hazardous debris was detected. Alternative trajectories were calculated that would take New Horizons further from Pluto, reducing the risk of collision at the cost of lower resolution observations. Fortunately, as the spacecraft approached and its cameras began to resolve the Pluto system in detail, no evidence of dangerous debris was found. The planned close flyby trajectory was confirmed safe, and New Horizons continued on its original course. The long cruise from Jupiter to Pluto was a test of patience for everyone involved. For most of the journey, the spacecraft was in hibernation mode, its systems powered down to conserve energy and reduce wear on components. The science team used this time productively, analysing data from the Jupiter encounter, refining observation plans for Pluto, and conducting ground-based observations to learn as much as possible about the target before arrival. During the cruise phase, observers on Earth used powerful telescopes to search for additional moons around Pluto and to identify potential Kuiper belt objects that New Horizons might visit after completing its primary mission. This search was remarkably successful, discovering the small moons Kerberos and Styx and identifying several candidate KBOs for a post-Pluto encounter. As the years passed and New Horizons drew closer to its destination, excitement began to build. The spacecraft emerged from its final hibernation period in December 2014, beginning the long process of preparing for the encounter. System checks confirmed that all instruments were functioning properly, that the spacecraft was healthy after its long journey, and that everything was ready for the historic flyby. In January 2015, New Horizons began its approach phase observations, capturing images of Pluto that were still little more than fuzzy blobs, but that represented the best views of the distant world ever obtained. Week by week, the images improved as the spacecraft drew closer. Features began to emerge from the blur, bright and dark regions, hints of surface markings, the first tantalizing glimpses of a world that had been a mystery for 85 years. The approach phase served multiple purposes. Scientifically, the observations provided valuable data about Pluto's rotation, surface features, and moons. Operationally, they allowed the navigation team to refine the spacecraft's trajectory, ensuring it would pass through exactly the right point in space at exactly the right time. And psychologically, they built anticipation for the main event, reminding everyone involved why they had worked so hard for so long. Because of the 9-hour round-trip time required for signals to travel between Earth and the spacecraft, the entire close encounter data collection sequence had to be programmed into New Horizons' computer to execute automatically. There would be no opportunity for real-time adjustments during the flyby. Every observation, every instrument activation, every data recording had to be planned in advance and uploaded to the spacecraft's memory. The flyby would unfold according to a precisely choreographed script with no room for improvisation. This autonomous operation was both a necessity and a source of anxiety. The mission team had done everything possible to anticipate problems and develop contingencies. But there was always the possibility of something unexpected. A software glitch, a hardware failure, an unanticipated hazard could all potentially derail the mission at the last moment. All the team could do was trust their preparations and wait. The final weeks before the encounter were intense. The spacecraft's cameras revealed Pluto in ever-increasing detail, showing a world far more complex and interesting than anyone had expected. A large, bright, heart-shaped feature dominated one hemisphere, immediately capturing public attention and earning the informal name, the Heart. Dark regions near the equator contrasted with bright polar caps. The surface appeared varied and geologically interesting, hinting at processes that scientists were eager to understand. On July 4, 2015, just 10 days before closest approach, New Horizons experienced a serious anomaly. The spacecraft's main computer detected a problem and automatically switched to backup mode, halting all science observations and entering a safe configuration. For several tense hours, the mission team worked to diagnose the problem and restore normal operations. The cause turned out to be a timing conflict in the spacecraft's command sequence, a software issue that was quickly resolved. But the incident was a stark reminder of how much could go wrong and how little margin for error existed. With the anomaly resolved, New Horizons resumed its approach observations. The images continued to improve, revealing features as small as a few kilometers across. Mountains, craters, plains, and strange terrain unlike anything seen elsewhere in the solar system emerged from the data. Each new image brought surprises, overturning expectations and raising new questions. The world watched as New Horizons approached its date with destiny. Media coverage intensified, with news outlets around the globe following the mission's progress. Social media buzzed with excitement as each new image was released. For a brief moment, humanity was united in wonder, sharing the experience of exploring a new world. Section 10, The Flyby, July 14, 2015, A Date with Destiny. July 14, 2015, arrived with a mixture of excitement and anxiety at the Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland, where the New Horizons mission was controlled. This was the day that 9.5 years of travel, decades of planning, and the dreams of generations would culminate in a few hours of intense observation. Everything the mission had worked toward came down to this moment. The flyby itself would be brief. New Horizons would pass within 12,500 kilometers of Pluto's surface, traveling at approximately 14 kilometers per second, or about 50,000 kilometers per hour. At this velocity, the spacecraft would cross the diameter of Pluto in just a few minutes. The entire close encounter, from the first high-resolution observations to the last, would span only about a day. There was no possibility of slowing down or entering orbit. The spacecraft carried nowhere near enough fuel for such a maneuver. This would be a one-time opportunity, a single chance to gather as much data as possible before New Horizons continued on into the outer solar system. The timing of closest approach was calculated with extraordinary precision. 11:49:57 UTC, July 14, 2015. At that moment, New Horizons would be closer to Pluto than any human-made object had ever been or likely ever would be again. The spacecraft's instruments would be working at maximum capacity, capturing images, spectra, and measurements that would transform our understanding of this distant world. But there was a catch. During the closest approach, New Horizons would be out of contact with Earth. The spacecraft's antenna could not simultaneously point at Pluto for observations and at Earth for communications. The mission team had made the decision to prioritize science over real-time contact, programming the spacecraft to focus entirely on data collection during the critical hours around closest approach. This meant that for about 22 hours, from the evening of July 13th to the afternoon of July 14th, no one on Earth would know whether the flyby had succeeded or failed. The last signal before the communications blackout arrived at Earth on the evening of July 13th. Everything appeared nominal. The spacecraft was healthy, its instruments were ready, and it was on course for the planned flyby. Then silence fell and the waiting began. The hours of the blackout were agonizing for the mission team. They had done everything possible to ensure success, but space exploration is inherently risky. A collision with an unseen particle, a software malfunction, a hardware failure, any of countless potential problems could end the mission in an instant. All they could do was wait and hope. At mission control, the atmosphere was tense but hopeful. Team members gathered to watch the clock tick down to closest approach, knowing that whatever was happening at Pluto was already in the past by the time they learned of it. The 9-hour communication delay meant that when the clock showed 11:49:57 UTC, the actual closest approach had occurred 4.5 hours earlier. New Horizons had already succeeded or failed, they just did not know which yet. The first signal after closest approach was scheduled to arrive at Earth at 02:52:37 UTC on July 15th, about 13 hours after the flyby. As that moment approached, tension at mission control reached its peak. Hundreds of team members, journalists and guests crowded into the auditorium, watching the screens that would display the first indication of the spacecraft's fate. The signal arrived exactly on schedule. New Horizons was alive and healthy. The flyby had succeeded. The room erupted in cheers, tears and embraces. 9.5 years of work, decades of dreaming, had culminated in this moment of triumph. Humanity had reached Pluto. The celebration was genuine but brief. There was work to do. The spacecraft had collected an enormous amount of data during the flyby, far more than could be transmitted to Earth in a short time. The slow data rate from Pluto's distance, combined with the limited power of the spacecraft's transmitter, meant that it would take 16 months to download all the data from the encounter. The first images and measurements were just the beginning of a long process of discovery. The initial data releases were carefully orchestrated to maximize public engagement and scientific impact. The first high-resolution image of Pluto, released on July 15th, showed the now famous heart-shaped feature in stunning detail. The bright, smooth planes that formed the left lobe of the heart were unlike anything seen elsewhere in the solar system, suggesting geological processes that no one had anticipated. Over the following days and weeks, more images and data were released, each one revealing new wonders. Mountains of water ice towered 3 kilometers above the surrounding terrain. Vast glaciers of frozen nitrogen flowed slowly across the surface. A hazy blue atmosphere extended far above the surface, backlit by the distant sun in images of breathtaking beauty. Pluto was not the dead, cratered world that many had expected. It was alive, dynamic, and endlessly fascinating. The flyby also provided detailed observations of Pluto's moons. Charon, the largest, proved to be a world of its own, with a dark polar cap, a vast canyon system, and evidence of past geological activity. The smaller moons, Nix, Hydra, Kerberos, and Styx, were revealed as irregularly shaped objects, tumbling chaotically in their orbits around the Pluto-Charon system. The scientific harvest from the flyby exceeded all expectations. Every instrument had performed flawlessly, gathering data that would keep researchers busy for years. The images alone numbered in the thousands, covering Pluto and its moons at resolutions ranging from global views to close-ups, showing features just a few tens of meters across. Spectra revealed the composition of the surface and atmosphere in unprecedented detail. Particle and plasma measurements characterized the space environment around Pluto, detecting the interaction between the solar wind and Pluto's escaping atmosphere. For Alan Stern and the New Horizons team, the flyby was the culmination of a lifelong dream. Stern had been advocating for a Pluto mission since the 1980s, facing countless setbacks and disappointments along the way. To finally see Pluto revealed in all its complexity and beauty was an emotional experience that transcended scientific achievement. This was exploration in its purest form, the expansion of human knowledge into realms previously unknown. The public response to the flyby was overwhelming. Images of Pluto dominated news coverage and social media for days. The heart-shaped feature became an instant icon, appearing on t-shirts, coffee mugs, and countless internet memes. People who had never thought much about planetary science found themselves captivated by this distant world, sharing in the excitement of discovery. The flyby also reignited the debate over Pluto's planetary status. Many people felt that the images from New Horizons proved that Pluto deserved to be called a planet, that a world so complex and fascinating could not be dismissed as a mere dwarf planet. The IAU's 2006 decision, already controversial, seemed even more questionable in light of what New Horizons had revealed. But regardless of how Pluto is classified, the flyby demonstrated something important about human nature. We are a species that explores, that reaches beyond the familiar into the unknown. The journey to Pluto, spanning nearly a decade and billions of kilometres, was an expression of our deepest impulses, our refusal to accept that some things must remain forever beyond our grasp. In reaching Pluto, we reached a part of ourselves, the part that looks at the stars and wonders what lies beyond. Section 11, Pluto revealed, mountains, hearts and glaciers. The data returned by New Horizons painted a picture of Pluto that was far more complex and dynamic than anyone had anticipated. Before the flyby, many scientists expected to find a cold, dead world, its surface frozen and unchanging for billions of years. What they found instead was a world of surprising geological activity, with features that suggested ongoing processes reshaping the surface even today. The most striking feature revealed by New Horizons was the vast heart-shaped region that dominates Pluto's encounter hemisphere. Informally named Tombaugh Regio in honour of Pluto's discoverer, this feature spans approximately 1,600 kilometres across and consists of two distinct lobes with very different characteristics. The left lobe of the heart, officially named Sputnik Planitia, is one of the most remarkable landscapes in the solar system. It is a vast basin filled with frozen nitrogen, carbon monoxide, and methane ices, forming a glacier that covers an area larger than Texas. The surface of Sputnik Planitia is extraordinarily smooth, with almost no impact craters visible, suggesting that it is geologically very young, perhaps less than 10 million years old. The smoothness of Sputnik Planitia indicates that some process is constantly renewing its surface, erasing the craters that should accumulate over time from meteorite impacts. Scientists believe this renewal occurs through a process called convection, in which warmer ice from below rises to the surface while cooler ice sinks, creating a slow churning motion that gradually erases surface features. The timescale for this convection is estimated at about 500,000 years, meaning the entire surface of Sputnik Planitia is replaced on geological timescales. The surface of Sputnik Planitia is divided into polygonal cells, each one tens of kilometres across, separated by shallow troughs. These cells are the surface expression of the convection occurring below, similar to the pattern seen in a pot of slowly boiling water. The centres of the cells are slightly higher than the edges, where cooler ice is sinking back into the interior. At the edges of Sputnik Planitia, the nitrogen glaciers flow outward into the surrounding terrain, filling valleys and lapping against mountain ranges. These glacial flows are remarkably similar to glaciers on Earth, despite being composed of nitrogen ice rather than water ice and existing at temperatures hundreds of degrees colder. The physics of glacial flow is universal, operating wherever ice exists in sufficient quantities and with sufficient slope to move under its own weight. The mountains surrounding Sputnik Planitia are among the most impressive features on Pluto. The Tenzing Montes and Hillary Montes, named after the first climbers to summit Mount Everest, rise up to 6 kilometers above the surrounding terrain. These mountains are composed primarily of water ice, which at Pluto's temperatures is as hard as rock and can support towering peaks. The presence of such tall mountains was unexpected. Before New Horizons, many scientists assumed that Pluto's surface would be relatively flat, lacking the internal heat necessary to drive mountain-building processes. The discovery of the Tenzing and Hillary ranges demonstrated that Pluto has been geologically active in the relatively recent past, though the exact mechanisms responsible for the mountains remain a subject of ongoing research. One possibility is that the mountains are blocks of water ice that have broken off from the edges of Sputnik Planitia and floated on the denser nitrogen ice, like icebergs floating on water. The nitrogen ice that fills Sputnik Planitia is less dense than water ice, so water ice blocks would float on its surface. Over time, these floating blocks could have accumulated at the edges of the basin, piling up to form the mountain ranges we see today. Another possibility is that the mountains were formed by tectonic processes, the cracking and shifting of Pluto's icy crust in response to internal stresses. Pluto's surface shows evidence of extensive faulting, with long cracks and ridges crisscrossing the terrain. These features suggest that Pluto's crust has been stretched and compressed over time, possibly in response to changes in the planet's interior. The right lobe of Tombaugh Regio, informally called the rough side of the heart, has a very different character from Sputnik Planitia. This region is covered with pitted terrain, where the surface has been eroded into a landscape of shallow depressions and irregular mounds. The pitting is thought to result from sublimation, the process by which ice transforms directly from solid to gas without passing through a liquid phase. As sunlight warms the surface, volatile ices sublimate away, leaving behind the more refractory water ice and creating the pitted texture. Beyond Tombaugh Regio, Pluto's surface displays a remarkable variety of terrains. The dark equatorial region, informally named Cthulhu Macula, after the fictional deity created by H.P. Lovecraft, stretches for thousands of kilometers along Pluto's equator. This region is covered with a layer of dark reddish material called tholins, complex organic molecules formed when ultraviolet light and cosmic rays break apart simple molecules like methane and nitrogen, which then recombine into larger, more complex structures. Tholins are found throughout the outer solar system, on moons like Titan and Triton, and on many Kuiper Belt objects. They give these worlds their characteristic reddish-brown coloration and may represent a form of prebiotic chemistry, the kind of complex organic chemistry that could potentially lead to the origin of life under the right conditions. On Pluto, tholins accumulate in the darker regions, where they are not buried by fresh deposits of bright nitrogen and methane ice. The boundary between the bright and dark regions of Pluto is often remarkably sharp, with the transition occurring over just a few kilometers. This sharpness suggests that the processes depositing bright ice and dark tholins are in a kind of dynamic equilibrium, with each process dominating in different regions depending on local conditions of temperature, sunlight, and atmospheric circulation. One of the most intriguing features discovered by New Horizons is a region of blade-like terrain near Pluto's equator. These blades, composed of methane ice, rise tens of meters above the surrounding surface and are oriented roughly east-west, like the teeth of a giant comb. Similar features, called penitentes, are found on Earth in high-altitude tropical glaciers, where they form through a combination of sublimation and solar heating. The discovery of penitentes on Pluto demonstrates that similar physical processes operate across the solar system, despite the vast differences in temperature and composition. Pluto's north polar region is covered with a cap of frozen nitrogen and methane, similar in some ways to the polar caps of Mars. This cap appears to grow and shrink with Pluto's seasons, as the changing angle of sunlight causes ices to sublimate in some regions and condense in others. The seasonal cycle on Pluto is extremely long, lasting 248 Earth years, so the changes observed by New Horizons represent just a snapshot of a much longer process. The variety of terrains on Pluto reflects the complex interplay of geological, atmospheric, and seasonal processes operating on this distant world. Far from being a simple ball of ice, Pluto is a dynamic planet with a rich geological history and ongoing activity that continues to reshape its surface. The data from New Horizons has provided a foundation for understanding these processes, but many questions remain unanswered, awaiting future missions and continued analysis. Section 12. Pluto's moons, a family of frozen worlds. Pluto is not alone in its journey around the Sun. It is accompanied by a family of 5 known moons, ranging from the substantial Charon to the tiny Styx. These moons provide valuable clues about Pluto's history and the processes that have shaped the outer solar system. Charon, the largest and closest of Pluto's moons, is a world unto itself. With a diameter of 1,212 kilometers, Charon is more than half the size of Pluto, making the Pluto-Charon system unique among planet-moon pairs in the solar system. The two objects orbit a common center of mass located in the space between them, leading some scientists to consider them a binary system rather than a planet and moon. Charon was discovered in 1978 by James Christie, who noticed a periodic elongation in images of Pluto that turned out to be a separate object. The discovery allowed astronomers to determine Pluto's mass for the first time and revealed that Pluto was much smaller than previously thought. Charon's name, suggested by Christie, refers to the mythological ferryman who transported souls across the river Styx to the underworld, a fitting companion for the god of the dead. New Horizons revealed Charon to be a fascinating world with its own distinct character. Unlike Pluto, which is covered with volatile ices like nitrogen and methane, Charon's surface is dominated by water ice. This difference in composition gives Charon a greyer appearance compared to Pluto's varied colours. The most striking feature on Charon is its dark polar cap, informally named Mordor Macula, after the Dark Land in J.R.R. Tolkien's Middle-earth. This cap is composed of tholins, the same complex organic molecules found on Pluto's dark regions. Scientists believe the tholins on Charon originate from methane gas that escapes from Pluto's atmosphere and is captured by Charon's gravity. At the cold polar regions, this methane freezes onto the surface, where it is transformed into tholins by ultraviolet radiation and cosmic rays. Charon's surface also displays evidence of past geological activity. A vast canyon system, informally named Serenity Chasma, stretches across the moon's equator, reaching depths of up to 9 kilometers. This canyon is part of a larger system of fractures that encircle Charon, suggesting that the moon's crust was stretched and cracked at some point in its history. One explanation for these fractures involves the freezing of a subsurface ocean. Early in its history, Charon may have possessed a liquid water ocean beneath its icy crust, kept warm by the heat of formation and radioactive decay. As this ocean gradually froze, the expanding ice would have stretched the crust, creating the fractures we see today. If this interpretation is correct, Charon joins a growing list of outer solar system bodies that may have once harboured liquid water. The southern hemisphere of Charon, which was in darkness during the New Horizons flyby, remains largely unexplored. The spacecraft was only able to image the northern hemisphere in detail, leaving the south as a mystery for future missions to investigate. Pluto's 4 smaller moons, Nix, Hydra, Kerberos and Styx, are much more modest objects. They range in size from Hydra, the largest at about 51 kilometres across, to Styx, the smallest at roughly 16 kilometres. These moons orbit further from Pluto than Charon, with orbital periods ranging from about 20 days for Styx to about 38 days for Hydra. The small moons were discovered relatively recently, with Nix and Hydra found in 2005 using the Hubble Space Telescope, and Kerberos and Styx discovered in 2011 and 2012 during searches for potential hazards to the New Horizons spacecraft. Their names continue the underworld theme established by Pluto and Charon. Nix is the goddess of night, Hydra is the many-headed serpent, Kerberos is the 3-headed dog guarding the gates of Hades, and Styx is the river forming the boundary of the underworld. New Horizons revealed the small moons to be irregularly shaped objects, more like potatoes than spheres. This irregular shape indicates that they lack sufficient mass for their own gravity to pull them into a round configuration. They are essentially large chunks of ice and rock, remnants from the violent event that likely created the entire Pluto moon system. One of the most surprising discoveries about the small moons was their rotation. Rather than rotating in a predictable manner, the small moons tumble chaotically, their orientation changing unpredictably over time. This chaotic rotation is caused by the gravitational influence of both Pluto and Charon, which creates a complex and ever-changing gravitational environment. The moons are essentially being pulled in different directions by the 2 larger bodies, preventing them from settling into a stable rotation state. The surfaces of the small moons are highly reflective, much brighter than expected. This high reflectivity suggests they are covered with relatively clean water ice without the dark tholins that coat much of Pluto and Charon. The reason for this difference is not entirely clear, but it may relate to the moon's small size and weak gravity, which would make it difficult for them to retain any atmosphere or capture escaping gases from Pluto. The origin of Pluto's moons is thought to be connected to a giant impact early in the solar system's history. According to this theory, a large Kuiper belt object collided with Pluto billions of years ago, blasting debris into orbit that eventually coalesced to form Charon and the smaller moons. This scenario is similar to the leading theory for the origin of Earth's moon, which is also thought to have formed from debris created by a giant impact. The giant impact hypothesis explains several features of the Pluto system. It accounts for the large size of Charon relative to Pluto, the circular and coplanar orbits of all 5 moons, and the similar compositions of Pluto and Charon. The impact would have been energetic enough to partially melt both bodies, allowing them to differentiate into cores and mantles, and potentially creating the subsurface oceans that may have existed on both worlds. The moons of Pluto represent a miniature planetary system, a family of worlds bound together by gravity and history. Studying this system provides insights into the processes that shaped the outer solar system and the violent events that occurred during its early history. The data from New Horizons has transformed our understanding of these moons, but many questions remain, awaiting future exploration. Section 13. The Atmosphere and Seasons of Pluto. One of the most surprising aspects of Pluto, revealed by New Horizons, was its atmosphere. Despite being so small and cold, Pluto possesses a thin but complex atmosphere that extends far above its surface and plays a crucial role in shaping the world below. Pluto's atmosphere was first detected in 1988 when astronomers observed the planet passing in front of a distant star, an event called a stellar occultation. As Pluto moved in front of the starlight dimmed gradually rather than winking out abruptly, indicating that it was being absorbed and refracted by an atmosphere. This discovery was unexpected, as many scientists had assumed that Pluto was too small and cold to retain any significant atmosphere. The atmosphere of Pluto is composed primarily of nitrogen, with smaller amounts of methane and carbon monoxide. These are the same volatile ices that cover much of Pluto's surface, and the atmosphere exists in a state of equilibrium with the surface ices. When sunlight warms the surface, some of the ice sublimates into gas, adding to the atmosphere. When the surface cools, gas condenses back into ice, depleting the atmosphere. This constant exchange between surface and atmosphere drives many of the processes that shape Pluto's appearance. The surface pressure of Pluto's atmosphere is extremely low, only about 10 microbars, or roughly 100,000th of Earth's sea level pressure. Despite this thinness, the atmosphere extends to remarkable heights above the surface, reaching altitudes of over 1,600 kilometers. This great extent is possible because of Pluto's weak gravity, which allows gas molecules to spread far from the surface before being pulled back down. New Horizons captured stunning images of Pluto's atmosphere backlit by the sun, revealing multiple layers of haze extending high above the surface. These haze layers are composed of tholins, the complex organic molecules formed when ultraviolet light breaks apart methane and nitrogen molecules in the upper atmosphere. The tholins gradually settle toward the surface, contributing to the dark reddish coloration of regions like Thule macula. The haze layers give Pluto's atmosphere a blue colour when viewed against the blackness of space. This blue colour results from the way small particles scatter light, preferentially scattering shorter blue wavelengths while allowing longer red wavelengths to pass through. The same process causes Earth's sky to appear blue, though the particles responsible are different. The atmosphere of Pluto is not static but changes dramatically over the course of its 248-year orbit around the Sun. As Pluto moves closer to the Sun during perihelion, increased solar heating causes more ice to sublimate, thickening the atmosphere. As Pluto moves away from the Sun toward aphelion, the atmosphere cools and begins to collapse, with gases freezing back onto the surface. This seasonal cycle has profound effects on Pluto's appearance. The distribution of bright and dark regions, the extent of the polar caps, and the thickness of the atmosphere all change as Pluto moves through its orbits. The Pluto, observed by New Horizons in 2015, was at a particular point in this cycle, having passed perihelion in 1989 and slowly moving toward the colder conditions of aphelion, which it will reach in 2113. Scientists have used computer models to simulate how Pluto's atmosphere and surface might change over the course of its orbit. These models suggest that the atmosphere could become significantly thinner as Pluto moves away from the Sun, potentially collapsing entirely during the coldest parts of the orbit. However, the exact behaviour depends on many factors that are still poorly understood, including the thermal properties of the surface and the distribution of volatile ices. The interaction between Pluto's atmosphere and the solar wind creates a complex space environment around the planet. The solar wind, a stream of charged particles flowing outward from the Sun, interacts with gases escaping from Pluto's atmosphere, creating a region of disturbed plasma that extends far downstream from Pluto. New Horizons detected this interaction, measuring the rate at which Pluto's atmosphere is escaping into space. The escape rate measured by New Horizons was lower than some pre-flyby predictions had suggested, indicating that Pluto's atmosphere is more stable than expected. Nevertheless, Pluto is slowly losing its atmosphere to space, with nitrogen molecules escaping at a rate of about 500 kilograms per second. Over the age of the solar system, this escape has removed a significant amount of material from Pluto, though the exact amount depends on how the escape rate has varied over time. The atmosphere also plays a role in transporting heat around Pluto. Winds in the atmosphere carry energy from warmer regions to cooler regions, moderating temperature differences across the surface. This atmospheric heat transport helps explain why Pluto's temperature is relatively uniform despite the large variations in solar heating between the equator and poles. One of the most intriguing aspects of Pluto's atmosphere is its potential for weather. The combination of volatile ices, atmospheric circulation, and seasonal changes creates conditions that could produce phenomena analogous to weather on Earth, including clouds, frost, and possibly even precipitation. New Horizons observed what appeared to be clouds in Pluto's atmosphere, though their exact nature remains uncertain. The study of Pluto's atmosphere has implications beyond understanding this single world. Pluto serves as a natural laboratory for studying atmospheric processes under extreme conditions, providing insights that can be applied to other bodies in the solar system and beyond. The complex chemistry occurring in Pluto's atmosphere, the formation of tholins, and the interaction with the solar wind all have parallels elsewhere, making Pluto a valuable case study for planetary science. Section 14. The continuing journey and legacy of New Horizons. The flyby of Pluto was not the end of New Horizons' mission, but the beginning of a new chapter. After completing its primary objective, the spacecraft continued deeper into the Kuiper Belt, searching for additional targets to explore. The vast reservoir of icy objects beyond Neptune offered countless possibilities for extended mission science. Even before the Pluto flyby, the mission team had been searching for suitable Kuiper Belt objects that New Horizons could visit after completing its primary mission. The search was challenging because the spacecraft had limited fuel for course corrections, meaning any target would need to be almost directly in its path. Using the Hubble Space Telescope and ground-based observatories, astronomers identified several candidate objects and ultimately selected one designated 2014 MU69. This small Kuiper Belt object, later officially named Arakoth, a word meaning sky in the Powhatan language, became the target for New Horizons' extended mission. Arakoth orbits the Sun at a distance of about 44 astronomical units, well beyond Pluto, making it the most distant object ever visited by a spacecraft. New Horizons flew past Arakoth on January 1, 2019, capturing images and data that revealed a remarkable object. Arakoth consists of two lobes joined together, giving it a shape reminiscent of a snowman or a peanut. The larger lobe is about 22 kilometers across, while the smaller lobe is about 14 kilometers. The two lobes appear to have come together gently, perhaps at speeds of only a few meters per second, and then stuck together, preserving their original shapes. The gentle merger that formed Arakoth provides important clues about how objects in the early solar system came together to form larger bodies. Rather than violent collisions, the building blocks of planets may have accumulated through gentle contacts, gradually growing larger over millions of years. Arakoth is a pristine remnant from this era, a fossil from the birth of the solar system that has remained largely unchanged for over 4 billion years. The surface of Arakoth is remarkably uniform, covered with a reddish material that is probably composed of tholins similar to those found on Pluto. There are few craters visible, suggesting that the Kuiper Belt is a relatively quiet place where collisions are rare. The uniformity of the surface also indicates that Arakoth has not experienced significant geological activity since its formation. The data from Arakoth complemented the Pluto observations, providing a broader picture of the Kuiper Belt and its inhabitants. While Pluto is large enough to be geologically active, with an atmosphere and complex surface processes, Arakoth represents the smaller, simpler objects that make up the bulk of the Kuiper Belt population. Together, these two targets span the range of Kuiper Belt objects, from the largest and most complex to the small and primitive. After the Arakoth flyby, New Horizons continued its journey outward, still returning data about the distant reaches of the solar system. The spacecraft's instruments continue to measure the properties of the solar wind, cosmic rays, and interplanetary dust at distances never before sampled by human technology. These measurements provide valuable information about the heliosphere, the vast bubble of solar influence that surrounds our star and protects the planets from the harsh radiation of interstellar space. As New Horizons travels ever further from the Sun, it joins an elite group of spacecraft venturing into the outer solar system. The Pioneer 10 and 11 probes, launched in the early 1970s, were the first to cross the asteroid belt and visit Jupiter and Saturn. The Voyager 1 and 2 spacecraft, launched in 1977, conducted the grand tour of the outer planets and have now entered interstellar space, the region beyond the Sun's magnetic influence. New Horizons follows in their wake, carrying the legacy of exploration into the 21st century. The spacecraft continues to function well, its systems healthy despite the rigours of deep space travel. The radioisotope thermoelectric generator that provides its power will continue to produce electricity for years to come, though the output gradually decreases as the plutonium fuel decays. Mission planners estimate that New Horizons will have sufficient power to operate its instruments until at least the mid-2030s, allowing continued observations of the outer heliosphere and potentially additional Kuiper Belt object flybys if suitable targets can be found. The search for additional flyby targets continues, though the challenges are formidable. New Horizons has limited fuel remaining, restricting the range of objects it can reach. The spacecraft is also moving away from the Sun at about 14 kilometers per second, meaning any target must be almost directly in its path. Despite these constraints, the mission team continues to search, using powerful telescopes to scan the region of sky ahead of the spacecraft for any objects that might be reachable. Even without additional flybys, New Horizons will continue to contribute to our understanding of the outer solar system. The spacecraft's dust counter, built by students at the University of Colorado, measures the density of microscopic particles in interplanetary space, providing data about the distribution of debris in the Kuiper Belt. The plasma instruments detect the solar wind and energetic particles, tracking how these phenomena change with distance from the Sun. And the cameras occasionally image distant Kuiper Belt objects, measuring their brightness and searching for moons or other companions. The legacy of New Horizons extends far beyond the data it has returned. The mission demonstrated that ambitious exploration of the outer solar system is possible, that a relatively small and inexpensive spacecraft can travel billions of kilometers and return transformative science. This success has inspired proposals for future missions to the Kuiper Belt and beyond, missions that would build on New Horizons' achievements and continue the exploration of this fascinating region. One proposed mission concept would send an orbiter to Pluto, allowing detailed study of the entire surface over an extended period. Unlike New Horizons, which flew past in a matter of hours, an orbiter could spend years mapping Pluto and its moons, observing seasonal changes, and investigating features that the flyby could only glimpse. Such a mission would be technically challenging and expensive, but the scientific return would be enormous. Other proposals focus on different Kuiper Belt objects, recognizing that Pluto and Arakoth represent only two examples of the diverse population inhabiting this region. A mission to Eris, the most massive known dwarf planet, would allow comparison with Pluto and provide insights into how size and composition affect the evolution of these icy worlds. A mission to Makemake or Haumea would explore objects with different characteristics, expanding our understanding of the range of possibilities in the outer solar system. The technological advances pioneered by New Horizons will benefit future missions regardless of their specific targets. The spacecraft's compact design, efficient power system, and autonomous operation capabilities provide a template for exploring distant objects where communication delays make real-time control impossible. The data compression and transmission techniques developed for New Horizons allow maximum science return despite the limited bandwidth available at such great distances. Perhaps most importantly, New Horizons has inspired a new generation of scientists and engineers to pursue careers in planetary exploration. The images of Pluto captured the public imagination in a way that few space missions have, reminding people of the wonder and excitement of discovery. Young people who watched the flyby in 2015 are now entering graduate school and the workforce, bringing fresh perspectives and new ideas to the field. The legacy of New Horizons will continue through their work for decades to come. The spacecraft itself will eventually fall silent, its power source depleted and its instruments dark. But it will continue travelling outward, a silent ambassador from Earth, carrying the memory of its creators into the void. Like the Pioneer and Voyager spacecraft before it, New Horizons will outlast the civilization that built it, drifting among the stars for millions of years, a testament to human curiosity and the drive to explore. Aboard New Horizons, the ashes of Clyde Tombaugh continue their journey, the discoverer of Pluto travelling further from Earth than any human remains have ever gone. It is a fitting tribute to the man who first glimpsed this distant world, who spent countless hours at the blink comparator searching for a point of light that moved. Tombaugh lived to see the space age dawn, but died before any spacecraft could visit his planet. Now, in a sense, he has made the journey himself, his remains carried by the same technology that fulfilled his dream of exploration. Section 15, The Geology of Pluto, A World in Motion. The geological complexity revealed by New Horizons transformed our understanding of what is possible on small cold worlds in the outer solar system. Before the flyby, many scientists expected Pluto to be a geologically dead world, its surface frozen and unchanging for billions of years. The reality proved far more interesting, with evidence of ongoing geological activity that continues to reshape the surface even today. The heart of Pluto's geological activity is Sputnik Planitia, the vast nitrogen ice glacier that forms the left lobe of Tombaugh Regio. This feature alone would be remarkable, but its implications extend far beyond its immediate boundaries. The presence of such a large, smooth, crater-free surface indicates that Pluto possesses internal heat sources capable of driving geological processes, a finding that was not anticipated before the flyby. The source of Pluto's internal heat remains a subject of active research. One possibility is radioactive decay, the same process that heats Earth's interior. Pluto's rocky core likely contains radioactive elements like uranium, thorium, and potassium, which release heat as they decay. Over billions of years, this heat could accumulate in the interior, driving convection in the ice mantle and powering the geological activity observed on the surface. Another possibility is that Pluto retains heat from its formation, the energy released when the planet accreted from smaller bodies in the early solar system. This primordial heat would have been substantial, potentially melting much of Pluto's interior and creating a global subsurface ocean. As this ocean gradually froze over billions of years, it would have released additional heat, prolonging the period of geological activity. The evidence for a subsurface ocean on Pluto is circumstantial but compelling. The location of Sputnik Planitia, almost exactly opposite Charon on Pluto's surface, suggests that the basin may have formed from an impact that was later filled with dense nitrogen ice. This concentration of mass would have caused Pluto to reorient, rolling over until the heavy basin faced away from Charon, a process called true polar wander. Such reorientation would be much easier if Pluto's icy shell were floating on a liquid ocean, decoupled from the rocky core below. Additional evidence comes from the fractures and faults that crisscross Pluto's surface. Many of these features appear to be extensional, formed when the crust was stretched rather than compressed. This stretching could result from the gradual freezing of a subsurface ocean, which would cause the ice shell to expand as liquid water transformed into less dense ice. The pattern of fractures observed by New Horizons is consistent with this interpretation, though other explanations are also possible. If Pluto does possess a subsurface ocean, it would join a growing list of worlds in the outer solar system where liquid water may exist beneath icy surfaces. Europa, Enceladus, Titan, and possibly Ganymede and Callisto are all thought to harbour subsurface oceans, making liquid water surprisingly common in the cold outer reaches of the solar system. These oceans are of great interest to astrobiologists who speculate that they might provide habitable environments for microbial life. The mountains of Pluto provide another window into its geological history. The towering peaks of the Tenzing Montes and Hillary Montes, rising up to 6 kilometers above the surrounding terrain, are composed primarily of water ice. At Pluto's temperatures, water ice behaves like rock, strong enough to support tall mountains without flowing or collapsing under its own weight. The origin of these mountains remains debated. One hypothesis suggests they are blocks of water ice that have broken off from the edges of Sputnik Planitia and floated on the denser nitrogen ice, accumulating at the basin's margins like icebergs piling up against a shoreline. Another hypothesis proposes that the mountains were uplifted by tectonic forces, pushed up as Pluto's crust stretched and faulted. A third possibility is that they are remnants of an older surface, isolated peaks that have survived while the surrounding terrain was buried or eroded away. The variety of terrain types on Pluto suggests a complex geological history involving multiple processes operating over different timescales. The smooth plains of Sputnik Planitia are geologically young, constantly renewed by convection and glacial flow. The cratered highlands of Cthulhu Macula are ancient, preserving a record of impacts accumulated over billions of years. The bladed terrain near the equator represents yet another geological regime, shaped by the sublimation and deposition of methane ice in response to seasonal changes in sunlight. The interaction between geology and atmosphere adds another layer of complexity. Volatile ices sublimate from warmer regions and condense in cooler regions, redistributing material across the surface over seasonal and longer timescales. This redistribution creates the bright and dark patterns observed by New Horizons, with fresh, bright ice accumulating in some areas while older, darker material is exposed in others. The glacial flows at the edges of Sputnik Planitia demonstrate that ice can move across Pluto's surface in ways analogous to glaciers on Earth. These flows carry nitrogen ice from the interior of the basin outward into the surrounding terrain, filling valleys and lapping against mountain ranges. The rate of flow is slow by terrestrial standards, perhaps a few centimetres per year, but over millions of years, these glaciers can transport enormous quantities of material. The cryovolcanism hypothesis suggests that Pluto may experience volcanic activity involving ices rather than molten rock. Features resembling volcanic constructs have been identified in New Horizons images, including a large mountain called Right Mons that may be a cryovolcano. If confirmed, cryovolcanism would indicate that Pluto's interior is even more active than the surface geology alone suggests, with liquid or semi-liquid material occasionally erupting onto the surface. The geological diversity of Pluto challenges our preconceptions about what small cold worlds can do. Before New Horizons, the conventional wisdom held that geological activity requires large size and internal heat, conditions that Pluto seemed unlikely to meet. The flyby revealed that this conventional wisdom was too narrow, that even small worlds in the outer solar system can be geologically dynamic if the right conditions are met. This lesson has implications for our understanding of other Kuiper belt objects and icy moons throughout the solar system. If Pluto can be geologically active, perhaps other similar worlds are as well. Future missions to the outer solar system may discover geological complexity in unexpected places, expanding our appreciation for the diversity of processes that shape planetary surfaces. Section 16. The Colours of Pluto, a palette of ices and organics. One of the most striking aspects of Pluto, revealed by New Horizons, was its colour. Far from being a uniform grey or white, Pluto displays a remarkable range of colours, from bright white to deep reddish brown, reflecting the diverse materials that cover its surface. The colours of Pluto arise from the interaction between different types of ice and the complex organic molecules called tholins. Understanding these colours provides insights into the composition and history of Pluto's surface, revealing processes that have operated over billions of years. The brightest regions on Pluto, including the heart-shaped Tombaugh Regio and the polar caps, are covered with fresh deposits of nitrogen, methane, and carbon monoxide ices. These ices are highly reflective, bouncing most of the sunlight that strikes them back into space. The freshness of these deposits indicates that they are constantly being renewed, either by condensation from the atmosphere or by glacial flow from reservoir regions. The nitrogen ice that fills Sputnik Planitia is particularly bright, giving the left lobe of the heart its distinctive appearance. This ice is relatively pure, without the contamination of darker materials that discolour other regions. The convection occurring within Sputnik Planitia may help maintain this purity, constantly bringing fresh ice to the surface while burying any accumulated contaminants. The darkest regions on Pluto, including the equatorial band known as Cthulhu Macula, are covered with tholins, complex organic molecules that give these areas their characteristic reddish-brown colour. Tholins form when ultraviolet light and cosmic rays break apart simple molecules like methane and nitrogen, which then recombine into larger, more complex structures. This process occurs primarily in Pluto's upper atmosphere, where the tholins form as a haze before settling onto the surface below. The accumulation of tholins on Pluto's surface is a slow process, requiring millions of years to build up the thick deposits observed in regions like Cthulhu Macula. The persistence of these deposits indicates that they are not being buried by fresh ice or eroded by geological processes, suggesting that the dark regions are among the oldest and most stable parts of Pluto's surface. The colour of tholins varies depending on their exact composition and the conditions under which they formed. Laboratory experiments have produced tholins with colours ranging from yellow to deep brown, depending on the starting materials and the energy sources used to drive the chemical reactions. The reddish-brown colour of Pluto's dark regions suggests a particular mix of organic compounds, though the exact composition remains uncertain. Between the bright and dark extremes, Pluto displays a range of intermediate colours reflecting mixtures of ices and tholins in varying proportions. Some regions appear pinkish, suggesting a thin coating of tholins over brighter ice beneath. Other regions show a mottled appearance, with bright and dark patches intermingled at scales too small for New Horizons to resolve clearly. The distribution of colours on Pluto is not random but reflects the interplay of geological, atmospheric, and seasonal processes. Bright ices tend to accumulate in regions where temperatures are coldest, such as the poles and the interior of Sputnik Planitia. Dark tholins accumulate in regions where volatile ices have sublimated away, exposing the underlying organic-rich material. The seasonal cycle plays an important role in redistributing colours across Pluto's surface. As Pluto moves through its 248-year orbit, different regions receive varying amounts of sunlight, causing ices to sublimate in some areas and condense in others. This redistribution can dramatically change Pluto's appearance over time, shifting the boundaries between bright and dark regions and altering the overall colour balance. Observations of Pluto from Earth over the past several decades have detected changes in the planet's brightness and colour, consistent with seasonal redistribution of surface materials. These changes are subtle but measurable, providing evidence that Pluto's surface is dynamic even on human timescales. The colours of Charon are distinctly different from those of Pluto, reflecting the Moon's different composition. Charon lacks the volatile ices that cover much of Pluto's surface, so it does not display the same bright whites and pinks. Instead, Charon appears predominantly grey, with a dark reddish polar cap that stands out against the neutral background. The dark polar cap on Charon, informally named Mordor Macula, is composed of tholins similar to those found on Pluto. However, the origin of these tholins is different. Scientists believe that methane gas escaping from Pluto's atmosphere is captured by Charon's gravity and freezes onto the cold polar regions. Once deposited, this methane is transformed into tholins by ultraviolet radiation, creating the dark cap observed by New Horizons. The smaller moons of Pluto, Nix, Hydra, Kerberos and Styx are surprisingly bright, much more reflective than Pluto or Charon. This high reflectivity suggests that the small moons are covered with relatively clean water ice, without the tholins that darken the larger bodies. The reason for this difference is not entirely clear, but it may relate to the moon's small size and weak gravity, which would make it difficult for them to retain any atmosphere or capture escaping gases from Pluto. The study of colours on Pluto and its moons provides a window into the chemical processes occurring in the outer solar system. The formation of tholins represents a form of prebiotic chemistry, the kind of complex organic synthesis that may have preceded the origin of life on Earth. By studying tholins on Pluto and other outer solar system bodies, scientists can learn about the conditions and processes that might lead to the emergence of life elsewhere in the universe. Section 17. Pluto in the cosmic context. Connections to other worlds. Pluto does not exist in isolation, but is part of a broader cosmic context that connects it to other worlds throughout the solar system and beyond. Understanding these connections helps us appreciate Pluto's place in the grand story of planetary formation and evolution. The most obvious connection is to the other Kuiper Belt objects that share Pluto's neighbourhood. As the largest known member of this population, Pluto serves as a prototype for understanding smaller KBOs that are too distant and faint for detailed study. The processes observed on Pluto, including cryovolcanism, glacial flow, and atmospheric escape, likely occur on other large KBOs as well, though perhaps at different scales or intensities. The dwarf planet Eris, discovered in 2005, is particularly interesting for comparison with Pluto. Eris is almost exactly the same size as Pluto, but significantly more massive, indicating a higher density and a greater proportion of rock relative to ice. This difference in composition may reflect different formation conditions or different evolutionary histories, providing clues about the diversity of objects in the outer solar system. Makemake and Haumea, two other large KBOs, offer additional points of comparison. Makemake appears to lack any significant atmosphere, unlike Pluto, suggesting that atmospheric retention depends on factors beyond size alone. Haumea's rapid rotation has stretched it into an elongated shape, demonstrating the range of physical forms that icy bodies can assume. Beyond the Kuiper belt, Pluto has connections to the icy moons of the giant planets. Triton, the largest moon of Neptune, is thought to be a captured Kuiper belt object, a world that originated in the same region as Pluto, but was later captured by Neptune's gravity. Triton's surface shows features remarkably similar to those on Pluto, including nitrogen ice plains, dark organic deposits, and evidence of cryovolcanic activity. The similarities between Pluto and Triton suggest that these worlds share a common heritage formed from similar materials under similar conditions in the outer solar system. Studying one helps us understand the other, even though they now occupy very different environments. Triton's proximity to Neptune subjects it to tidal heating and gravitational stresses that Pluto does not experience, providing a natural experiment in how environment affects the evolution of icy worlds. Europa and Enceladus, moons of Jupiter and Saturn respectively, offer another point of comparison. These worlds are thought to harbour subsurface oceans beneath their icy crusts, maintained by tidal heating from their giant planet hosts. If Pluto also possesses a subsurface ocean, as some evidence suggests, it would demonstrate that liquid water can exist in the outer solar system even without tidal heating, sustained instead by radioactive decay and residual heat from formation. The presence of complex organic molecules on Pluto connects it to the broader question of life's origins in the universe. Tholins, the reddish organic compounds that colour Pluto's dark regions, are thought to be similar to the organic materials that accumulated on early Earth, providing the raw materials for the emergence of life. By studying tholins on Pluto and other outer solar system bodies, scientists can learn about the chemical processes that might lead to life elsewhere. Pluto also has connections to comets, the icy wanderers that occasionally visit the inner solar system. Comets are thought to originate in the Kuiper belt and the more distant Oort cloud, making them cousins of Pluto in a sense. The volatile ices that cover Pluto's surface, nitrogen, methane and carbon monoxide, are the same materials that form comet nuclei and produce the spectacular tails that comets display when they approach the Sun. The study of Pluto thus contributes to our understanding of comets and their role in delivering water and organic materials to the inner planets. Some scientists believe that comets played a crucial role in the origin of Earth's oceans, and perhaps even the origin of life, making the connection between Pluto and comets relevant to our own existence. Looking beyond the solar system, Pluto provides a template for understanding exoplanets, worlds orbiting other stars. Many exoplanets discovered in recent years are thought to be ice-rich worlds, similar to Pluto, orbiting in the cold outer regions of their planetary systems. By studying Pluto in detail, we can develop models and expectations for these distant worlds, even though we cannot observe them directly. The diversity of exoplanetary systems discovered so far suggests that ice-rich worlds like Pluto may be common throughout the galaxy. Some of these worlds may be larger than Pluto, perhaps large enough to retain thick atmospheres and support complex geological activity. Others may be smaller and simpler, frozen relics from the formation of their planetary systems. Understanding Pluto helps us imagine the range of possibilities that exist among the countless worlds orbiting other stars. Pluto's place in the cosmic context reminds us that our solar system is not unique, but is one example of a common phenomenon: planetary systems forming around stars throughout the galaxy. The processes that shaped Pluto, accretion, differentiation, geological activity, atmospheric evolution, are universal processes that operate wherever the right conditions exist. By studying Pluto, we learn not just about one small world, but about the fundamental principles that govern planetary formation and evolution throughout the universe. Section 18. The Future of Pluto Exploration. The New Horizons flyby was a beginning, not an end. The data returned by the spacecraft has raised as many questions as it has answered, inspiring scientists to dream of future missions that would explore Pluto in even greater detail. The most ambitious proposal is a Pluto orbiter, a spacecraft that would enter orbit around Pluto and study the system for years rather than hours. Such a mission would allow complete mapping of Pluto's surface, including the hemisphere that was in darkness during the New Horizons flyby. It would enable long-term monitoring of atmospheric changes, seasonal variations, and geological activity, and it would provide detailed observations of all 5 moons, revealing features too small for New Horizons to resolve. The technical challenges of a Pluto orbiter are formidable. Entering orbit around Pluto would require slowing down from the high velocities needed to reach the outer solar system in a reasonable time, a maneuver that would consume enormous amounts of fuel. Various solutions have been proposed, including aerocapture using Pluto's atmosphere, gravity assists from Charon, and advanced propulsion systems like nuclear thermal rockets or ion engines. The time required to reach Pluto is another challenge. New Horizons took 9.5 years to reach its target, and an orbiter might take even longer if it needed to carry the fuel required for orbital insertion. Mission planners must balance the desire for quick results against the practical constraints of spacecraft design and propulsion technology. Despite these challenges, studies have shown that a Pluto orbiter is technically feasible with current or near-term technology. The scientific return would be enormous, justifying the investment required to develop and launch such a mission. Several concept studies have been conducted, exploring different approaches to the problem and identifying the key technologies that would need to be developed. A less ambitious but still valuable option would be a Pluto flyby mission carrying more advanced instruments than New Horizons. Such a mission could target different regions of Pluto, observe the system at different points in its seasonal cycle, or carry instruments designed to answer specific questions raised by the first flyby. Multiple flybys over time would build up a more complete picture of Pluto than any single mission could provide. Another possibility is a mission to one of Pluto's smaller moons, perhaps a lander that would touch down on Nix or Hydra and study the surface in detail. These small moons are poorly understood, and a dedicated mission would reveal their composition, structure, and history. Such a mission would be technically challenging due to the moon's small size and irregular shapes, but it would provide unique insights into the formation and evolution of the Pluto system. The search for additional Kuiper Belt objects to explore continues as well. New Horizons demonstrated that even small primitive KBOs like Arakoth can be scientifically fascinating, and there are countless other objects in the Kuiper Belt waiting to be visited. Future missions might target objects with different characteristics, such as binary KBOs, objects with unusual colours or compositions, or objects in different orbital classes. The development of new propulsion technologies could revolutionize outer solar system exploration. Nuclear thermal propulsion, which uses a nuclear reactor to heat propellant, could significantly reduce travel times to the outer planets and beyond. Solar sails, which use the pressure of sunlight for propulsion, could enable missions to the outer solar system without the need for heavy fuel loads. And advanced ion engines, which accelerate propellant using electric fields, could provide the sustained thrust needed for orbital insertion at distant targets. The future of Pluto exploration also depends on continued public interest and political support. Space missions are expensive, and funding decisions are made by governments responding to the priorities of their citizens. The enthusiasm generated by New Horizons demonstrated that the public cares about planetary exploration. But maintaining that enthusiasm over the long timescales required for outer solar system missions is a challenge. Education and outreach play a crucial role in building support for future missions. By sharing the excitement of discovery with the public, scientists can inspire the next generation of explorers and build the constituency needed to fund ambitious missions. The images and data from New Horizons have been widely shared, appearing in classrooms, museums, and media around the world. This outreach helps ensure that the legacy of New Horizons will include not just scientific knowledge, but also public engagement with the wonders of the cosmos. The future of Pluto exploration is bright, filled with possibilities that would have seemed like science fiction just a few decades ago. The small distant world that Clyde Tombaugh discovered in 1930 has become a destination for human curiosity, a place where we have sent our machines and our dreams. Whatever missions the future may bring, Pluto will continue to captivate our imagination and inspire our desire to explore.